Okay, good morning, Astronomy 1010. Welcome back to our third lecture, where we will be finishing lecture 1 and moving into lecture 2. And today we're actually going to work on our first homework assignment, homework 1. So we've got a 1.5 hour lecture, 1.5 hour lecture, followed by a little homework session. Last week we discovered that it was nice to take a little pause between the lecture and the homework. So I'll try to build in maybe 10 or 15 minutes just for you all to take a little cool down cruise before we do the homework sesh, okay? I discovered some things this weekend. I discovered that grading 160 papers times 2 was not fun. That was not a good time. It took a long time and it was painful. Because of this, I'm going to really need to lean on you guys here to get your work in on time. And I want to say something about this right at the beginning of the video when I have everyone's attention. In the past, when I had smaller numbers of students, I could try to work with people, you know, if they screwed up really bad, I'd try to help them get some late homeworks in. But I'm going to have to kind of clamp my foot down to keep this machine from grinding to a halt. I can't imagine what this weekend would have been like if all kinds of people were turning stuff in late on top of what I was already trying to manage. It would have been insane. I'm really, really concerned about that. And I know people screw up. I myself have a long history of screw ups, so I'm very sympathetic. But if you think about it, I'm doing the labs with you and I'm doing the homeworks with you. And ideally, I'd want you guys to upload them as soon as we're done, because you'll be done, and that's how we all can go to sleep at night. But I know sometimes people have to go to work, like Frank had to go to work last class, and so he had to do the lab. Did you ever get that lab done, Frank?
Yeah, I did. I turned it in on Thursday.
Good man, good man. But the rest of you cats, especially I'm talking to some night students who will be watching this video later, it's okay to take an extra day or so to get that submitted, but I need to grade those papers on the weekend, on Sunday. And so I think what's going to happen is Monday morning, I'm gonna close the books on homework 1 and lab 1. Do you guys understand? Like Sunday night at midnight or something, I'm just going to have to say that's it. And if you missed it, you got to take a 0 and move forward. Because what's going to happen is if you couldn't manage to get it together to do that week's work, what happens when that week's work snowpiles into the next week's work? It's going to create a huge mess. I don't like having a lot of rules in this class. I pride myself in having as few as possible, but I think those late homeworks and labs are going to have to be one. And it's not my fault. There's too many of you. Do you guys understand? So if for some reason you ever miss a lab or a homework, you got to be thinking to yourself, what is it? Today's Wednesday, right? If you had theoretically missed today's homework, you got to be thinking, I got to get that on Thursday, the latest Friday, and Saturday is your Hail Mary pass. Do you see what I mean? Because I want to grade on Sunday, and then I want to be done with that week, and I want to move on. So if you guys can work with me on that and understand what I'm talking about, that'd be super helpful. Nothing's beyond negotiation, but I can't have huge numbers of people turning in crazy stuff at all random times. It'll be nuts. Okay, so I'm laying down the law, and that's what I got to say. If you have any comments or questions about that, I'm open-minded to discussion here. If not, let's talk about astronomy. We got a lot to learn today. I believe last class we learned a little bit about the small angle formula, didn't we? So someone tell me what the small angle formula is all about. Maybe I can get a little diagram to help jog your memory. I don't know. Here's a picture of the small angle formula. What does the small angle formula tell me? Oh, geez, not everyone at once. You know, raise your hand or something.
It's we don't see sizes, we see angles, and this is how we measure things versus how we see them.
Is that Christian? I like what you're saying, buddy. What's the angular? Do you know the angular size of the moon?
5 degrees.
Not 5 degrees. Divide by 10.
Oh, 0.5 degrees.
Good. Do you know what the angular size of the sun is?
Also 0.5 degrees.
Yeah.
Sorry, yeah.
That's good. That's good coinkeeping. Hey, Christian, since you're a person who remembers things, I always like talking to people who can remember things. Did we talk about eclipses?
Yes, we did. And then we also talked about the eclipses where the moon sometimes appears to be smaller than the sun.
The annular eclipses. Good.
Yeah.
Christian, you got a nose for news. But Christian, I have a much more elaborate lecture on eclipses that I may try to get to today, or maybe I'll do it next class. But stay tuned. You're going to learn more about that stuff, okay? All right.
Okay.
So Christian remembers that the angular size of the sun and moon are both 1/2 degree. But you guys also remember that degrees aren't really great units of angle to use in astronomy. Remember that I showed you a picture that my friend took. Where's that picture? It was the picture of the 3 brightest objects in the nighttime sky. Well, okay, Mars technically would be one of the brighter objects as well. But we've got Sirius, the brightest star in the sky. We've got Jupiter here, and we've got Venus there. I don't know if you guys have been looking up during this past weekend, but there are not 1 or 2, but there are 3 very bright planets in our sky right now. This weekend, I noticed the moon in conjunction with Mars, and it was pretty dope, actually. I think it was maybe Saturday night. I was taking a walk with a friend, and we looked up and we could see the moon, and Mars was like a big red dot right above it. It just looks kind of cool. Sometimes when you see 2 famous astronomical objects next to each other, it's kind of neat. And so Mars is up in your sky right now. Mars is kind of red. You'll also see a very bright Jupiter, which is orange. Or actually, Jupiter's kind of yellow. Saturn's kind of orange. Mars is very red. So there's lots of planets for you to see in the nighttime sky. Don't be afraid to look up, you know. Don't be afraid to put your new astronomy knowledge to the test. See if you can measure the angular size of the moon by holding your finger at arm's length. See if you can identify some of these objects. And you know what? If you can't, get one of them damn apps on your phone, like the night sky, and then point it around and start learning how things work. You'll discover that it's fun and it's a good party conversation starter. Okay, so it's worked for me anyways. Remember that we can't just use degrees, because the angular size of the moon, which is the largest object in your nighttime sky, is, when I say largest, I mean largest in angular size, right? Obviously the moon's not the biggest astronomical body, but the moon and the sun have the largest possible angles that anything that has an angle can have in your sky. Things like planets and, God forbid, stars, they require much smaller angles. So in addition to degrees, we have arc minutes. You'll remember that an arc minute is a 60th of a degree. So 1 degree is 60 minutes of arc. And an arc second, this is all just a little review of what we learned last time. I'm trying to prime the pump here to get you back in the mood. So arc seconds, 1 arc minute is 60 arc seconds. So you'll see me use this today. Arc minutes are the single tick mark. Arc seconds are the double tick mark, or the quotation mark. And stop me if you heard this one before, but as I mentioned, an arc minute is kind of like looking at a soccer ball from half a mile away. Students, do you believe that you could make out the black and white pentagram checkered pattern on a soccer ball from half a mile away? I mean, what's a half a mile? It's like, Matt, you're saying no, you don't think so? You don't think you'd be able to make, I don't think you'd be able to make out those checkers either, but it would be close. The human eye can see down to a limiting angle of 3 to 4 minutes of arc. It doesn't really matter if the thing that you're looking at is close to you or far away. It could be a little paramecium floating around in your eyeball. It could be a quasar at the edge of the observable universe. If it's bigger than 3 minutes of arc, you'll be able to see it. If it's smaller than 3 minutes of arc, it will be too tiny to see, okay? For instance, here's an idea. The planet Jupiter, it turns out, subtends roughly 1 minute of arc. And the reason why I think that's funny is, suppose we had lived in a solar system where Jupiter had formed with just a bit more mass and had been a little bigger. If Jupiter had had a diameter that was 3 times bigger, instead of Jupiter being essentially a star on our sky, we might have actually seen Jupiter as a small disk. We might have actually been able to see the little cloud stripes of the planet floating in the sky. That probably would have looked pretty awesome. Unfortunately, we grew up in a universe where only the sun and moon can be resolved, all right? And in fact, I'm going to say one more thing about that before we get started here. In optics, we distinguish between 2 classes of objects. This is something you can't find in the textbook. This is something you have to learn from an astronomer, okay? There is a difference between a resolved object.
Okay. Is he here?
Hey,
No.
hey, Chatty Cathy,
Let's see.
you might want to mute yourself. I don't know
Let me
what.
see.
Beatrice? Unless you want to talk to me about angular size, okay? All right, maybe I can mute her. I don't even know if she knows what's going on. Okay, seems to have stopped. Anyways, a resolved object is an object like the sun or like the moon, right? The sun or the moon can be seen as a disk on your sky, and that means your eye can distinguish between the top of the disk and between the bottom of the disk. You'll also notice that if you look at the moon, you can see like the dark maria, so you can actually make out features. This is what a resolved object is like. It's one in which the angular size can be resolved by the detector, which in this case is your eye. An unresolved object, did I tell you guys this last time? I don't think I did. No, okay, good. So an unresolved object is one which is, for all intents and purposes, a mathematical point. And stars kind of fall under this category. You can detect light from an unresolved object because the star is bright, but you can't make out any features and you can't see the disk. Astronomers or people in optics, they sometimes refer to this as a point source, okay? The easiest way to learn the difference is for me to kind of, I don't know, give you a test here to see if you understand what I'm talking about. So let's start with the picture I showed a moment ago. Sirius, Jupiter, Venus. Are these objects resolved or unresolved in the photograph?
Unresolved.
Excellent. They're unresolved because they are point sources. Now we zoom in with a small telescope. We reveal Jupiter, the 4 Galilean moons, Io, Europa, Ganymede, Callisto. And here you can see Venus in what's probably a waxing gibbous phase. I'll teach you the phases of the moon, maybe even today if I have time. That's a classic astronomy thing to learn. Venus happens to go through phases just like the moon does. Class, is Jupiter resolved or unresolved in this image?
Resolved.
Good, you can see it as a disk. In fact, sometimes you can even see the little stripy cloud tops. How about the moons?
Unresolved.
Excellent. How about Venus?
Resolved.
It's resolved, or you would not be able to see that shadow there. You wouldn't be able to see any features. Cool, so it's, yes, okay, nice, Ava. It seems like you guys understand what I'm talking about, and that's always a happy thing, okay? So now you've learned something about optics. The angular size of Jupiter seen here in this image is about 1 arc minute. That's roughly the angular size. So if I were to, in fact, let me use my little tricky drawing tools here. If I were to look at Jupiter from Earth, it's going to subtend a really, really, really tiny angle. But that angle is pretty darn close to 1 minute of arc. Now, you'll notice that the moons have a much smaller angular size. That's where the arc seconds tend to come into play. Planets can be expressed, their angular sizes, in terms of arc minutes. But once you start getting into stars, once you start getting into moons, then you need a real damn tiny angle, and that's where your arc seconds come in. So you break an arc minute into 60 pieces. An arc second is kind of like trying to look at a dime from 2.5 miles away. That is a truly small angle. And for comparison, the supergiant star Betelgeuse, think about how tiny the angular sizes of stars are. If I go back to slide 1, 2, 3, whatever it is, remember that Betelgeuse is the famous red star in the upper shoulder of Orion. Not only is this one of the largest stars in our local galaxy, but this is actually one of the biggest angular size stars as well. This picture, Ava, is from the PowerPoint slides, and I should have made them available to you. Actually, I'm using my Astronomy 1020 slides right now, but this picture is in the 1010 version of PowerPoint show number 1. If you want, I can make this. Okay, if you're going to ask me the number, I can tell you, but I might have to open up the 1010 version for you. And by the way, sorry, let me share my screen so you guys can see what I'm doing here. Ava's asking a question about the slides. I provide them all to you guys. I'm actually going from my Astronomy 1020 numbers in space, which I could provide to you. In your version, Ava, it's Lecture 1, the nighttime sky. Orion is the first picture, slide 1. As to those angles, I sure hope they made it in there. Yeah, slide 33, 34, 35, those are the slides I'm on now. My 1020 slides have a couple extra in there, so that's why I tend to use this one. I should probably make them both the same. Hopefully. Okay, perfect. Good. I've made her happy. That makes me happy. Anyways, what I was trying to say was the star Betelgeuse, right? The angular size of this star is 0.55 arc seconds, or 55 milli-arc seconds. Compared to a disk like the sun or the moon, stars are so insanely tiny in their angular size that the light that they give us is a microscopic pencil-thin beam. And for this reason, the turbulence of the atmosphere can cause stars to twinkle and dance around in the sky. I'm sure you guys have noticed this before. If you look up at the nighttime sky and you look at stars, they seem to dance around and they change colors, the twinkling of stars. And by the way, when you're out looking at stars and planets tonight, here's an important rule or difference between planets and stars. Stars twinkle, planets don't, okay? That's how you'll tell the difference. That's a cool little takeaway that you can bring home with you, and it'll help you identify planets in your sky tonight. All right. Now that we have mastered angles, now that we've revisited angles, it's time for us to use those angles to sort of make a model of the nighttime sky and to develop some stellar coordinates so we can track the motions of stars across our sky. And we're going to do this by making a model of the nighttime sky that's similar to the one that the Greeks had in mind. Greek philosophers, Greek astronomers, they believed that Earth was the center of the cosmos, and they believed that the stars were affixed to a crystalline sphere which rotated around the Earth. Now, today we know that this is not true. Earth is not the center of the solar system or the galaxy or the universe or anything for that matter. However, even though the stars might lie at a variety of distances from us, trying to think about all of that at once is not helpful. You need to sort of simplify the problem so you can just understand how the nighttime sky rotates. And so in that case, thinking of the celestial sphere as this rotating crystalline sphere around Earth is actually a helpful concept. It'll help you begin to learn how the nighttime sky rotates. Oops. Sorry, I just gave this whole operation a kick here. Okay, so let's begin with a slide of what it is I'm trying to talk to you all about here. Just going to zoom ahead. I'm here today to talk to you about the celestial sphere, for starters. And here's a little model of the celestial sphere. Let's take a peek at it before we take our notes. We have Earth in the center. We're going to pretend like all of the stars are stuck to the sphere. We have a couple of key points: the north celestial pole, the celestial equator, and the south celestial pole. Let's go into note mode. The celestial sphere is a useful lie. It could be defined as a sphere of infinite radius on which stars, planets, suns, well, sun, moon, and even galaxies seem to rotate. So we're just going to pretend like they're all stickers on a rotating sphere. Question? We got another chatterbox out there. I'll find you, and I will mute you. You've been muted. Okay. Let's see here. How do I hide the non-video participants? Just a second, guys. Oh, it's in here. I want to hide the trolls so I can focus on the people who are sharing video with me. Okay. Let's identify a few points. Can't read the board. That means we're having the cameras blurry. Okay, Katie, thanks for that heads up. I can fix that, but you have to give me a second here. If I open up my Logitech settings, I can deactivate autofocus. The autofocus is extremely irritating. And I think if I get this autofocus worked out, that'll stop that from happening. So Katie, bear with me here for a second while this slow, dumb program loads. Okay. All right, autofocus is now deactivated. Let's see. Katie, can you read it now? Maybe I can turn the lights down a bit. It's better. Okay, good. Yeah, hopefully we can stop that autofocus. Let me know, guys, if you have trouble reading this. There's no point if you can't read what I'm writing. Okay, so some key points on the celestial sphere. We have the north celestial pole. The north celestial pole is the projection of the North Pole onto the sky. Then we have the celestial equator. The celestial equator is projection of Earth's equator onto the sky. And then last but not least, the south celestial pole, which is the projection of the South Pole onto the sky. Let me see here. I'm just going to fiddle with this. Sorry about my handwriting. When I write fast, I don't tend to write neatly. Let me give a second for you guys to catch up. It looks like Yin Chen is still writing. Thirsty business here. Okay, how are we feeling? Can I go forward? Give me some thumbs up. Anyone need a second here? Oh yeah, Adam, we got you. Okay, Cam. Let's give Adam a second to catch up. Adam, you thumbs up me when you're ready to go. Where are you? Okay.
I have a question.
I'd love to answer it.
Are there like degrees with either of these poles? Are there like the celestial pole, is it similar to like the same degrees with the North Pole?
Your question needs cleaning up for it to make 100% sense.
Yes.
But no, it's okay. Sometimes learning how to talk to each other about this stuff is part of the process. The North Celestial Pole is a point on the sky.
Okay.
The South Celestial Pole is a point on the sky. As such, because they are mathematical points, they do not have angular size. They are just a dot. But what I think the question was, if I can kind of reinterpret your question, I think you may have been asking me, is there a way to figure out what their position or location is on the sky?
Yeah, like longitude and latitude.
Yes, but wait, who am I talking to so I can get to know your voice here? Who am I chatting with?
Amber.
Oh, hi, Amber. Okay, I can see you now. I had to just scroll. I can only see a few boxes at a time. Amber, the reason why you might have had trouble formatting that question is that's what we're going to do today. Today, I'm going to teach you how to describe their positions and actually how to find them in the sky. So what we're doing right now, Amber, is you're learning these terms about the fact that there is a North Celestial Pole. And what I'm going to do very quickly after that is I'm going to make a model of the sky, and I will teach you how to find the angles at which you can find them from the ground. And in that sense, your question will make sense because there is a number of degrees up from the horizon that we will find the North Celestial Pole. So stay tuned. You're anticipating me. We're going to get there. But I want to build it up slow and careful. Okay, I'm going to erase this now. It seems like you guys have had enough time. Am I using the right camera today? I am using the right camera. Okay, maybe I just need to clean it with Windex or something. All right, let's erase this and let's move on here. Oh, actually, no, we are not ready to move on. I have one more note to make about the celestial sphere, but I need to make some real estate. This is an important point that is not obvious when you're first learning this stuff. So let's put a big exclamation point next to it, okay? You can always see exactly 1/2 of the celestial sphere in your, wait for the fancy vocabulary term here, local sky, where local sky is a key concept in astronomy. You can always see 1/2 of the celestial sphere in your local sky. Write that down. All right. Let me show you what I mean by that, okay? Click, okay. I want to share screen and I want to show an important slide. That statement needs some explanation, and this is the picture to do it, all right? You tend to think of yourself, let me get a better color here, like yellow. You tend to think of yourself as a little dude standing on a big Earth. Let's imagine that you're a little dude. Let me get orange here. And let's imagine that you're standing right about here, where this yellow arrow is. If you're standing on the Earth halfway up the globe, like you do in Rhode Island, you tend to imagine that you're a little dude surrounded by this little dude sky. But in fact, you are a little dude who is surrounded by this big dude sky up here. If you have no buildings or trees in your way, if you're either standing on a perfectly flat field or a desert, or maybe you're on a boat in the ocean, your local sky, the sky that you see at night, is a dome or a hemisphere, and it actually encompasses exactly 1/2 of the celestial sphere. The reason why that can look confusing in this picture is that this picture lies to you a little bit. It makes the Earth look kind of big in comparison to the size of the celestial sphere. But in fact, the Earth is extremely tiny and the sphere is of infinite radius. In other words, if this picture were to be drawn a little better, the way that picture should look is it should look like a massive celestial sphere, and Earth should just be a microscopic dot in the center. So that if you're standing at some particular latitude, like if your head is here, then your horizon encompasses a line that goes right through the middle of Earth. There is no difference between a line going through the middle of Earth and a line going through your feet. So all of this, all of that is what you see in your local sky. That's not obvious unless someone explains it to you. And I think that's important because it helps you realize that stars, when they rise and set, it's a little different depending on which star, but they should be up for close to 12 hours. You should have a star up in the nighttime sky for 12 hours. You should have the day up for 12 hours. It's not exactly like that. It depends upon latitude and such. But roughly, if you have a star here, an observer located at this arrow would be able to see that in their local sky. Even if there was a star located right here, they'd be able to see it. All right, I wanted to make that clear. Now that I have, presumably, it's time for us to make a model of the local sky and identify some key features of it. Let's imagine that you did step out on a very flat plain in the desert so that there were no obstructions. Your sky would be a dome, a hemisphere, and there would be a number of key locations that we can use to describe the positions of stars. This is so important that I think we're going to have a little Bob Ross time here together, and we're going to make a 3D model of our local sky. You may remember that I told you guys that having a ruler would be helpful. How many of you actually busted one of these things out or found one of those? Hey, all right. Hey, I just recognized whoever is abate_000, is it Andrew? Is that right? Andrew, can we change your name to Andrew so that I get to memorize your face and your name? If you're you know, a21369@hotmail.com, it's hard for me to get to learn your names and your faces. This is actually one of the cool things about the whole Zoom class is every time I look at your face, Juan or Gabriella or Matt, I can see your names with your face, and that's helping me get to know you guys. So I appreciate it. Actually, to that effect, it's Alex and Jake, right? And Alex is on the left and Jake is on the right?
Yeah, Alex is on the right, Jake is on the left.
Oh, sorry, yeah.
It's
Sorry,
all
it might have been reversed here. So
do you want me to put both of our names in here when I log on?
I'm doing it for you, Alex and Jake. Yeah, I got you. All right, that's cool. That just helps me, all right? So thank you guys for helping me learn your names, all right? All right, if you have that ruler, it's time for us to do art, okay? And if you don't, well, you're gonna have to get creative. You're gonna have to use the edge of your calculator or something, okay? So we're gonna make a 3D model of your local sky. Follow along with me. I'm just gonna up the brightness a smidge. Okay. So this is a 3D view of the local sky. Whoops. Man, it's doing that focus thing again. I don't understand. I turned you off, so you need to behave. Okay. First thing I'm going to do is I'm going to make a line. I'm going to leave myself a lot of headroom. If you guys are actually using a ruler that has centimeters, you might want to make yours about 12 centimeters or so on the page. I've got to make mine a little bigger, so I'm going to make mine about So I'm going to make mine 60 centimeters. That's what I'm going to do. So I'm going to draw a line 60 centimeters in length. And I'm actually going to measure the midpoint, which for me is 30 centimeters. And I'm going to put a dot at the midpoint, okay? Next thing I'm going to do is I'm going to make a line that is 30 centimeters. I'm going to put a dot 30 centimeters, the same radius, up above. And this is because I'm going to want to draw a dome. Here's a cool trick on how to make a nice dome. Since I know that half of this line is 30 centimeters, I'm going to make dots 30 centimeters from the center at a bunch of different places. That way I know what my dome should pass through. That's kind of a little trick, a little art trick that might help us here. So a circle or a semicircle should always have the same radius. So I can use that fact to figure out what points I should pass through. Okay, so this is a little overkill here, but now I'm going to try to make the best damn dome possible by connecting the dots. How about that, huh? That don't look too bad. Now, let's go ahead and give some three-dimensionality to this. I want you to put a dash a little bit above and a little bit below that dot there, okay? And then we're going to connect the edges to those dashes to kind of make an oval that looks like the ground. A little lumpy here, so I'm going to fix that. Okay. In fact, if you're feeling really artistic, I'm feeling very artistic this morning, I think I'm going to even shade in some grass so that I can see that I'm sitting on a field somewhere. So I'll put some happy little grass on my dome so that I can really see what a three-dimensional sky I'm standing under here, okay? There's a nice 3D view of our local sky, and we now have to label some parts to it. I'm going to sip water while you catch up to me. I have to atone for my sins last night. Okay. Now, this is a very important step. When you draw your 3D view of the local sky, it's important that you pick some cardinal directions. And I can't stress how important this is. I am a right-handed person, so by convention, I always choose the right side to be north, and I always choose the left side to be south. And that means that towards the plane of the board over here is going to be east, and into the plane of the board is going to be west, okay? I think that's a good way to do things. I like to have a right-handed bias because it just seems natural. You're drawing so bad, Heva. Well, Heva, using a ruler will help, and you will get better at this, okay? I'm not really great at art, but I've drawn enough of these where I realize you do get better over time. Better to start somewhere. By the way, Ava, you will notice that in your lecture handouts for Lecture 2, I actually gave you this picture. But I still think you should try to draw it because trying to draw it is good for you, okay? Now listen, something I want to warn you about. Those of you who have the textbook should be wary that the textbook tends to do things in reverse. When they show you drawings of the local sky, they, for some reason, always like to put north on the left-hand side, probably because their drawings were made by some sort of sinister left-handed artist, okay? You know, those artists tend to be left-handed. And that's fine if you're a sinister left-handed artist. You can put north on the left-hand side, but I think you're going to get confused because some of my best pictures do not come from the book, but I think this is a fantastic picture, and this also has a north right-hand bias. So I think we should all, until you guys learn a little bit better, we should always try to take this convention together, okay? All right. Now that you've made your local sky, it's time to identify what are called the 5 fundamental positions of your local sky. So let's start by making a dot directly. Oh, by the way, so our observer, the observer dude, is standing here in the field. If you want, you can put a little observer in the center of the field. Let's put a dot right at the top of the dome, and let's label that dot with a Z. The point directly over your head is called the zenith. Next, we have our horizon, or our horizon ring, okay? The horizon is a 360-degree ring at the base of the local sky. You will notice that the zenith is at a right angle, a 90-degree angle to all points along the horizon, okay? So I can make a 90-degree angle between the zenith and any single point along the horizon. Next up, we have a vocabulary term for this arc right here. This arc that runs from north to south through the zenith is called the meridian. And the meridian is an important vocabulary term for you guys. And the meridian is defined as an arc that rises due north it reaches the zenith and sets due south. And you'll notice that I've underlined due north, zenith, and due south because those are the key points along the meridian. If you want, we can draw a line from the horizon there, and we can draw a line to the meridian up to there, okay? Just to help you see where it is in the diagram. Let me try to show you where we're going here. Here's a picture. Here's something for you to think about. Slide 79. Sorry, hold on. I hit the wrong damn button. Slide 79. Oops. Oops. All right, there we go. The meridian here on this picture is an arc that goes from north up through the zenith and down to the south. It's kind of like the equivalent of a 12 o'clock hand if you think of the sky like a giant clock. During the course of the night, stars will rise in the east somewhere on your eastern horizon. In our sky, they kind of come up at an angle into the south. They cross the meridian here at the highest point of their journey through the sky, and then they sink back down into the west. And they kind of travel on these arcs that look like this. We're going to eventually describe them. The rising and setting of stars, this nightly motion that they make, they're called diurnal circles. That's kind of like some fancy vocab there. So let me, do I have a place here? I'm going to put it down here. Diurnal circles. You can think of diurnal circles as star tracks. Okay, they're the tracks that stars make as they rise and set in the sky. Our goal, Amber, if I remembered you right. I don't even know where you are, Amber, but you're hiding there somewhere. Our goal, Amber, is to be able to describe the motions of these stars intelligently using fancy vocabulary terms that we paid money to learn, okay? And let's start here. We have two more fundamental positions of our local sky. Class, oh, that's great. Yeah, there's some clashy words. You know, Amber, astronomy is a really old science. It's thousands of years old. It's older than science, the concept of science itself. It's older than astronomy. It's older than physics, even though today it has a lot to do with those things. And because it's so old, astronomy has the magic, the spider web of time woven over it, and it's very clashy, you know? So learning these vocabulary words is very nice for your education. All right, so if I'm located in the Northern Hemisphere, class, do you think I should be able to see the North Celestial Pole? Let's go back a few slides to where we looked at that local sky again. Where are you, baby? Here we go. So suppose I'm standing in Rhode Island. Should I be able to see the North Celestial Pole in my local sky? What does instinct tell you? Jake says yes.
Yes.
You'd be correct. As those of you who said yes are correct. Because anywhere above the equator, you're going to see 1/2 of the celestial sphere, and that will, usually the rule of thumb is this. If you're in the northern hemisphere of Earth, you can see the North Celestial Pole. If you are in the southern hemisphere of Earth, you can see the South Celestial Pole. The only way you could see both North Celestial Pole and South Celestial Pole at the same time would be if you were exactly on the equator. And even then, even a little tree or a rock would obscure them from your view because they're going to be on your horizon, all right? Since we're in the northern hemisphere, let's do a 3D view of the northern sky so that it reminds us of what Rhode Island is like. I'm going to draw an arrow towards the North Celestial Pole. I'm going to make a line from the foot of my observer about halfway up the sky, so you guys can kind of do the same thing. And boom. Okay, there we go. And this is the North Celestial Pole, so I'll abbreviate it as NCP. And I don't know if you guys know this, but there is a famous object which resides at the North Celestial Pole. Anybody know what that is? I can see you mouthing it.
Northern Star.
It is the North Star. Though a couple of you said that. Does anyone know the proper name of the North Star? It's an actual, it has its own. Sorry?
Is it Polaris?
Very good. Who said that? Where are you?
Katie.
Who's me? Oh, Katie, yes, sorry. There's so many little boxes. I have to like scan around to see who's what. Yeah, Katie, right. It's Polaris. Now, let's see. Oh, okay. Yes, Heva, very hard words for a non-native English speaker. And I sympathize with this. I had a hard enough time learning astronomy in my native English tongue. So I have deep appreciation for students who have English as a second or third or fourth language. So feel free to get some extra attention from me if you need me to re-explain something. I also tend to speak in some very goofy colloquialisms. I tend to use idiosyncratic. I'm trying not to use fancy words here. I tend to speak weird because I am weird. So I'll try to tone that down. Okay. Okay, anyways, let's take a peek. Just pretend for a moment that this is the class you thought it was going to be, where you were going to like learn the names of the stars and the constellations. Boy, were you wrong about that. But just for a second here, we're going to pretend, and I want to do a little riff on Polaris in case those of you don't know it. If you go out at night, okay, most of you can probably find the Big Dipper, because it's usually up in your sky, and the stars in the Big Dipper are very bright. They're all very bright. So I can see them from downtown Providence. And the Big Dipper is actually part of a constellation called Ursa Major, the Big Bear. And here, these stars here are the tail of the bear. It's the handle of the Dipper, but it's the tail of the bear. These stars are the butt of the bear. And there are some other parts of the bear too. Like he's got like a long snout, and then he has some claws, but those stars, so these are supposed to be his claws, and I think this is supposed to be his snout. But those stars are kind of faint, so most people won't be familiar with them. Now, the front two stars of the Big Dipper are known to astronomers as the pointer stars, because if you go out at night and find the Big Dipper, if you make a line connecting the pointer stars, it will kind of take you up to Polaris. And I'm telling you this so that you can find Polaris on your own if you step outside tonight. Polaris is not the brightest star in the sky. It is not a particularly brilliant star. It's just a little dirtbag star, just a little nobody star that you've probably looked past a million times without thinking much about it. But you can find it if you use these pointer stars to locate it. Polaris will not be over your head unless you are at the North Pole with Santa Claus, okay? For most people, the North Star is not directly over your head. It's just somewhere in your northern sky. Let's put that star on the sky. By the way, when I put stars on the dome, you'll notice I actually put them on the curve of the dome. That's important. Polaris is on the sky. Just for your own edification, just so you know things, it's true that Polaris is part of its own constellation called Ursa Minor, the Little Bear. But these stars are quite faint and very difficult to see. If I'm standing at a rooftop downtown Providence where it's very light polluted, I can easily see Polaris, but it's not super bright. And I can see this star, whose name is Kochab. And I have to admit, I've forgotten the name of this star, but I can see that star too. These stars I cannot see from Providence, nor can I see them from the observatory in Warwick. I can see them just about if I go to my dad's house in Smithfield, and I can definitely see them if I go to Block Island. So if some of you are down in South County and you live in a dark sky, you might actually be able to make out the Little Dipper. If you go out to the deserts of Texas or Arizona, this thing will blaze. It'll pop right out at you. So in a light polluted sky, you might have a hard time seeing the Little Dipper, but you can always see the Big Dipper because all of these stars are very bright. So I challenge you, go out and see if you can use those pointer stars and find Polaris on your own. We should also be able to see the celestial equator in our local sky. And let's go to the picture that I showed you before, that the model that we're trying to emulate here. Here we go. The celestial equator is a line that runs east to west. It's always at a 90-degree angle with respect to Polaris, and it kind of cuts through your southern sky. Let's see if we can do that together. I'll use red. I'm going to actually take my ruler and try to make a 90-degree angle. Okay. And I'm going to put a dot up here. This part is always really hard for me, drawing the celestial equator. And I'm going to draw a horseshoe that goes west to east through my local sky. That's about as good as I can do free-handed. So see what you can do there. That's always been tough for me. Label this as CE. This is your celestial equator. Also, we've already defined celestial equator and north celestial pole, but let's put them down here, okay? So we have the north celestial pole. And we have the celestial equator. Taken together, the zenith, the horizon, the meridian, north celestial pole, and the celestial equator make up what are called the fundamental positions of your local sky. These are fancy vocabulary terms, which you can say with or without your jaw moving, that help you understand how to describe things that travel through your sky. And I'm going to use these terms all the time going forward. Probably the newest one for you guys is the Meridian. Okay, I'm just giving a moment for everyone to catch up to me because now that we've done all this hard work, I need to erase it. I also need to keep track of time. I think we're doing okay. I'm just going to look around the squares here and see who's still writing. Andy, let me know when you're done. Cam, you need a second? Okay, Cam, give me a thumbs up when you're done. All right, Andy's done. All right, Cam's done. Anyone else need a minute here before I erase this stuff?
Can I have a minute?
Yes, sure. I'll sip some water. Whoever that was, just let me know when you're done.
Okay, I'm done. Thank you.
All right, here we go. Now, we've learned how to talk intelligently about the local sky. Now it's time to follow up on the promise that I made to Amber. Amber wants to know, how to find, for instance, Amber, I think the question that you were trying to ask me earlier is, how many degrees above the hoo-ha will I find Polaris? First, we had to establish that the hoo-ha is the horizon, okay? We have to say horizon. And yes, there is a specific angle that this star is located from the horizon, and we need to learn to talk about that. So we're gonna have to develop coordinates to describe the positions of stars. And this may take us into the next class. I wanna show you the top-down view of what we're gonna do. We're gonna attempt to learn 3 coordinate systems in this class. And the first couple are, we're going to learn about equatorial, let me try this again. We're going to learn geographic coordinates first. This is stuff that you've heard about before. Geographic coordinates are latitude and longitude. They help you locate where you are on Earth. Remember, students, where you are on Earth determines what the stars are going to do in your sky. The rotation of the sky is very different from the equator to the North Pole to Rhode Island. So we have to kind of first make sure we know how to talk about where we are. And then we're going to have 2 coordinates for the sky. We're going to use the horizon system. The horizon system is the coordinate system that you want to use for the local sky, to describe stars in your local sky when you're out observing with your friends. And then we need a more professional coordinate system to talk to other astronomers around the world. And these are, well, actually, it's more useful even than that, but the third coordinate system is equatorial coordinates. This is what we're going to build up to. The equatorial coordinates, you can think of them as being used for the global sky. They're kind of like a latitude and a longitude, but for stars. Now, each of these things is going to take a minute for me to describe. What I suspect is going to happen is I suspect that today, my lecture today will cover these 2. And I'm guessing that in our next class, I'll probably have to get to this one. And that'll actually work out because next class, we're going to use equatorial coordinates for our lab. We're actually going to be doing a lab that uses the celestial sphere, and that's actually a pretty fun lab. All right, so this is a little roadmap of what I've got to do with you guys. Let's tackle 1 and 2 and see where we're at. Okay. Introducing geographical coordinates. Hey, Something that I want you guys to keep in mind when we talk about coordinates on Earth and on the sky, don't forget that geographical coordinates are angles. And we measure them in in degrees, arc minutes, and arc seconds, okay? And the two coordinates that we use for the Earth, let's take a look at our Earth here, right? Earth is a ball, but it is a spinning ball. And the spinning of Earth gives us a unique line, the equator, which allows us to divide the Earth into a northern hemisphere and a southern hemisphere. We're going to use this to base our geographical coordinates. And the angles, which I'm sure you've heard about before, are latitude and longitude. Sometimes people use a mnemonic device. Lines of latitude are like a ladder. Lines of longitude run up and down like tangerine slices, okay? Latitude is defined as your degrees north or south of the equator. For example, the North Pole would have a latitude of 90 degrees north. Notice that when we specify latitudes, we need an angle and a direction. Unless you're on the equator would be 0. We can write that in too if we want. Okay, longitudes are tricky because unlike latitude, if longitudes are tangerine slices that run like this metal ring from north to south and they measure east to west, there's kind of no natural starting point for longitudes because they're all kind of the same. So we decided to get together with some astronomy friends, and some astronomy friends got together and decided that they were going to specify the 0th lines of longitude as passing through the front door of the Royal Greenwich Observatory in Greenwich, England, which is just outside of London, okay? And the so-called prime meridian, the 0th line of longitude, would run right through the front door of the Royal Greenwich Observatory. And what this means for you is if you ever take a trip to England, you can visit the Royal Greenwich Observatory and you can stand on this line and you will have 1 foot in the Western Hemisphere and 1 foot in the Eastern Hemisphere, and then you can take a selfie for the gram, okay? So this is what people do. They sometimes visit the prime meridian, they visit the Royal Greenwich Observatory. As a matter of fact, friends, one of my former students actually visited the Royal Greenwich Observatory after learning this in my class. And she brought back to me my very own prime meridian pencil from the Royal Greenwich Observatory gift shop. This is now a treasured item on my cart, okay? No one gets to borrow my prime meridian pencil. So feel free to bring me some gifts and presents when you visit the Royal Greenwich Observatory. All right, so how do we define our longitude then? We define longitude as your degrees measured east or west of the so-called prime meridian, which passes through England, among other places. It's a good idea for you to have a vague sense of your own coordinates on Earth. So let's lay out the latitude and longitude for Providence, Rhode Island, which is pretty close to just about everywhere else in Rhode Island since we're such a small state. Rhode Island has a latitude of about 42 degrees north, and Rhode Island has a longitude of 71 degrees west. So we are 42 degrees north of the equator, 71 degrees west of England. Hey, I don't know how to do this on a Google phone, but if you have an iPhone, why don't we try something right now just for kicks? Do you guys have that compass app? I think it comes pre-installed on your phone, right? Somewhere on my phone, I have a compass app, all right? You guys have this? And what's cool is underneath, it actually tells us the latitude and longitude where we're at. And I want you guys to check out mine for a second. I may have to adjust my focus here. Let me see if I can hold this up. It's a little blurry, but I bet if I manually focus it, I can. There we go. Okay, can you guys see, remind me to fix that afterwards, how on my compass, it gives me not only my latitude and longitude in degrees, but you can see my arc minutes and arc seconds. I bet some of you have a different number than me because we're not all located at the, so this is something cool that we can do, make use of our different locations. Is anyone right now located in South County, far from Providence? No? No one's down in like a southern town in the state here? You're all kind of close to me? I've got 41 degrees, 49 minutes of arc, and 22 arc seconds. Katie, what do you have?
I have 41 degrees, 49, and then 25.
Okay, so we are 3 arc seconds north or south of each other. My longitude is 71 degrees, 24 minutes of arc, 47 arc seconds.
Ooh.
What are you?
I'm 71 degrees, 33, however you say that. Is that arc minutes?
Arc minutes.
And 22 arc seconds.
So you are more west than me. So I suspect you're out in Johnston or Smithfield.
Yep.
Yeah, did I get it right? Cool. That's why they pay me the big bucks. All right, so no one's significantly south here? No.
No.
No, okay. That's cool. Hey, neighbor. Oh, you are Noah? Noah, do you have this thing up? What does it say on yours?
I'm at 41, 36, 49.
Okay, so you're south from me. So you're a few arc minutes south. And what's the longitude?
71, 8, 30.
Oh, wow. So are you like in the bottom left in the state, or what do you call those? Like Hope, Rhode Island, or what's down in the corner there? Where are you?
I'm in like it's next to Newport, kind of.
Oh, Little Compton. Yeah, I know. Little Compton's magical, man. That place looks like Middle Earth. It's so beautiful there.
It's nice out here, so.
I go to Goosewing Beach. Sometimes I like to go to Goosewing Beach.
Oh, yeah.
Piping plovers. All right. All right. So, anyways, cool. So, hey, I think and Heva's 41, 46, and 71, 25. So, I think the thing that I was trying to get at there, if I was doing anything, was even to go top to bottom from Rhode Island, we're all basically at the same number of degrees, but to go from the top of Rhode Island to the bottom of Rhode Island is a change of maybe 10 arc minutes or something like that. 41, 42. Yeah, so Cam, you're kind of close to me. But I think Noah was the furthest away that I could find in the class. And he was about 10 or so arc minutes south of me. So even to just cross Rhode Island, you're only crossing a few arc minutes, a dozen arc minutes of, 26. Oh, Cam, that is, I'm sorry, you're significantly east of me, I guess. No, sorry, a little bit west of me. Anyways, hey, I got I got to fix my focus here because this isn't cool no more. So listen, one last question. There is a line on the opposite side of the prime meridian. Do you guys know what it's called? What do we call the opposite of the prime meridian?
Yeah.
So it goes through the other side of Earth. It goes like on the back side. Anyone know?
The equator.
No, the equator is a line of latitude, constant latitude. This is a line of constant longitude. It's known as the International Dateline. The International Dateline is the name of the longitude that's opposite the prime meridian. And the idea is that it cuts through the backside of Earth. And what's important about the International Dateline is it sets the boundary between days on Earth. So if you think about it, since the Earth is constantly rotating, at some point you've got to cross the boundary from Tuesday to Wednesday, right? Because the sun is constantly rising at new longitudes on Earth. So we have to decide, where does the day start on Earth? And we've decided that the day should start when the sun crosses the International Dateline. The importance of that is you can take a business trip from Japan to California, and when you cross the International Dateline, you may actually go back in time by a day, going from east to west. You'll also notice that the International Dateline does a little wiggle for political reasons, which are probably obvious, right? Like, you wouldn't want the International Dateline to cut through the middle of Fiji or Tonga, because if you were the mailman in one of these sorry towns, then you'd have to be delivering mail to one side of the street and it would be Tuesday, and on the other side it would be Wednesday. That would get a bit messy. So for political reasons, they kind of wiggle around Fiji, Tonga, and American Samoa. But for the most part, it's the International Dateline is at a longitude of 180 degrees. Anyways, welcome to Earth. Now you know some things about your own planet, all right? If the latitude of the North Pole is 90 degrees north, what's the longitude of the North Pole? What would be the longitude of the North Pole?
Would it be 0 degrees?
Well, sort of, but if you look at this picture, you can see it's a little bit more complicated than that.
Is it 180?
Once again, it's not that you're wrong, it's just that you're not exactly right. Okay, so yes, 0 degrees does go through the North Pole, and 180 degrees goes to the North Pole.
Possible value?
The trick question, Brendan.
Yes, Joel knows it's a trick question. He can see that all lines, several of you are noticing that all the lines of longitude are passing through the North Pole. That means it's multi-valued or it's undefined. It's what we call in mathematics a degenerate point. So the longitudes break down at the North Pole and the South Pole, but that's okay because the latitude uniquely specifies your position. So the longitude of the North Pole is undefined, or as we say in mathematics, degenerate. Okay? So there's more fancy terms for you guys. All right. You've now learned as much as I could possibly teach you about geographical coordinates. You know how to find your way around Earth, and you even have a little compass app to help you locate yourself. I'm going to do some erasing here. Everyone, anyone need an extra second here? Okay. Matt, you good? All right, I'm erasing.
Don't be picking on me with this stuff now, Brendan.
Say that again, Joel?
Don't be picking on me with this stuff now. If you remember, I had some trouble with this stuff over the summer. Don't be picking on me.
Well, so one of the nice things about taking my Astronomy 1010 class and my Astronomy 1020 class is the beginnings of the two classes are sort of the same. It's kind of like you have to go up the same tree trunk and then the classes diverge. But this stuff on celestial coordinates can be some of the hardest material in the class. So getting a second exposure to it really helps to kind of make it firm. You'll discover that in Astronomy 1010, Joel, we do a lot more coordinates. And our next few lectures are going to be about timekeeping and calendars. It's all a subsection of astronomy that's called astrometry. Positioning, timekeepings, calendars. They're all related. So stay tuned for more of that. Okay, introducing our first coordinate system, a simple coordinate system known as the horizon system. The horizon system is how to talk smart about the positions of stars when they are located in your local sky. That means you and your Grammy out at the telescope together, all right? The angles are altitude and azimuth. The altitude of a star is the degrees above the nearest horizon. Degrees above the, I'm going to put this in parentheses. It almost doesn't need to be said, but sometimes it does. Degrees above the nearest horizon. So the idea is if you're in your local sky, cue up the slide, please. If you're in your local sky and you see a star, you start on the closest point on the horizon and you measure how many degrees up from the ground is it, okay? This star might have an altitude of 40 degrees or so, based on what I can see there. The azimuth is defined as the degrees along the horizon measured clockwise from north. And that means azimuth is a little bit like direction. It's kind of like north, south, east, west on the horizon, okay? So in the case of this star, it's helpful to know the angles in a unit circle here. This star's closest point on the horizon is right there. So to measure its azimuth, I would start due north and I would swing along the horizon like so, measuring in degrees until I got to that point. Can anyone out there think they can estimate roughly how many degrees it would be from here all the way around to there? Who knows their unit circle? I'm sorry, could you say that one more time?
Like maybe 270 or something like that.
Yeah, so it goes 0, 90, 180, 270 would probably, this is kind of a perspective drawing, so 270 might be there. So I would actually even give it a little bit extra, maybe even 300. Because it doesn't quite look like this is a 90-degree angle here. But in any case, to help you learn the azimuths, we could list the azimuths of north, south, east, and west. So due north is 0 degrees. Due east, 90 degrees. Due south is 180. And due west is 270. What's the altitude of the zenith?
Zero degrees?
90.
Zero?
The altitude of the zenith.
90.
90.
Zero.
90, right? It's degrees above the horizon. So if the zenith is here, right? You got to go 90 degrees to get up to it from the horizon. What's the azimuth of the zenith? What is the azimuth? Sorry?
Is it undefined?
Who said that? Where's that smarty pants? Who got
No.
that? Was that Noah?
Yeah.
Hey, look what Noah knows. Noah can see that every point along the horizon is equidistant from the zenith, right? It's equal distance from every point on the horizon up to the zenith. So that point must also be degenerate or undefined. Nicely done, sir. We'll put that in here. Just for the hay of it, okay? Okay. You guys have taken your first steps into a bigger world. Now, I want you guys to remind me something, because we're going to take a little kids break here before we get into our homework session today. Joel, if you're around on Monday, or whoever's around on Monday, or maybe I'll just watch my own damn video. Next class, we're going to start off by playing the alpha, beta, gamma, delta game. And
Oh, God.
I'll tell you what that is next time. The next class, we're going to practice our horizon system coordinates.
Not fun.
I was freaking out.
I remember that game.
Yep. Every one of my students has to learn it. Okay, so let's talk about what happens now, friends. We are about to do homework number 1 together. We are going to make it awesome. We're going to make it beautiful, but it's going to take some work. We're going to have to work at it, okay? So in my other class, before we did the first homework, the students got a little pause just to get a drink or whatever you have to do, you know? Do you guys like that idea? You want to take a little 10-minute break here before we get into it? All right, Ava likes it, so I like it. So I'll pause the recording. Do not let me forget to start the recording when I come back. I'm just going to like eat a little piece of a sandwich and have a iced tea, and then I'll be ready to do the homework. This is the most important part of the day. Remember, I grade you on these assignments, so we got to do this work and we got to turn it in when we're done. So take a little break, and I'll see you guys a little bit after 1, okay? I'll be here. I'll be floating around if you need me. Okay, we're back. It's time for homework 1, and I was just telling the class that I'm extending the deadline. So homework 1 and lab 1, you can turn them in up to this weekend. But after Sunday, I'm going to close the submissions for homework 1, lab 1, because we'll be moving into our next week of work, and I don't want to get them mixed up. I also need to warn you guys that I have to do a verification of enrollment reporting. And the way I do that is I look to see who's turned in a homework or a lab. As long as you've turned in a homework or a lab, you'll be safe. But any student who has neither turned in homework 1 or lab 1 will be reported as a no-show, and they will be dropped from the course. So you cannot afford to screw around on this. I'm also not going to be very excited about letting you back in because I have too many of you already. So if you're not pulling your weight, if you're not doing your work, you're just going to create problems for yourself and me down the line. Keep in mind that we do the work together. So all you have to do is just hang out with me and it'll all be fine, all right? You just have to spend some time doing this stuff with me. But I want to warn you guys about that. So make sure you've got something submitted if you plan on staying in the course. Okay. Here's what we're going to do.
And it's as easy as that.
Yep.
Took them over the summer, and it's you show up, pay attention, do the labs and the homework with them, and turn it in. And it's that easy.
There you go. Don't take my word for it. Joel's been through the paces here. As have a couple of you. Greg has taken my class, my other version of the course as well. Okay, here's what we need to do. We need to get the questions ready. So let's go to our Blackboard page and let's navigate to the homework tab. And under the homework tab, here's the problems we're going to be doing. Chapter 2, number 44, 48, 53, 57, 59. I've even provided you guys with the questions in case you don't have your books together yet. I'll try to do that every time. This is the page from the textbook that I've scanned, which I believe has all of the questions. So I need to write these numbers down. Let me show you guys how I want your homework to be set up so that you understand what I'm looking for. I'd greatly prefer it if you did it in pencil so there's not too much scratch outs. If you're very neat, you can do it in pen. Very neat. At the top of your page, don't forget to put your name, okay? AS1010. And I'd like you to put whatever your section is. Some of you will be in 001. Some of you are in 002. Some of you are in the night class, which is 101. Also, very important when you write me emails that you say, hi, my name is Katie. I'm in astronomy 1010 section, whatever it is, so that I know like what class you're in when I'm talking to you. Somewhere up there, we could also put, this is homework number 1. We're going to be doing chapter 2. The numbers are, let me go back to that share screen for a second. 44, 48.
53, 57, and 59.
Okay, cool. Sorry, I put a Hungarian wax pepper in my tomato sandwich and it spiced up my life a little bit here, so I'm dying. Okay, so I like it when you guys read out the questions. Joel, you know the drill, so if you've got the questions handy, why don't you take us out and read us chapter 2, number 44, and the title as well.
All right, it's a new planet. Planet in another solar system has a circular orbit and an axis tilt of 35 degrees. Would you expect this planet to have seasons? If so, would you expect them to be more extreme than the seasons on Earth? If not, why not?
So this is our givens. We're told it's a new planet with a circular orbit and a 35-degree tilt. They've asked us 3 little sub-questions. Will the planet have seasons? Will they be more or less extreme than Earth, and why? I'd like you guys to know from the get-go that when I grade these problems, every problem is graded out of 5 points. And I usually have preconceived ideas of what each points are worth. In this word problem, a couple of points for whether you address this correct, a couple of points for this, and 1 point for the why. So let's see what you guys learned from our 2 lectures thus far. Will a planet with a circular orbit and a 35-degree axis tilt, will it have seasons, yes or no?
Yes.
Yes. So we will write yes. A planet with a 35-degree axis tilt will have seasons. This is kind of an easy question. This is your starting question, so I'm going easy on you. Okay, there's some points. Will they be more or less extreme than Earth? What do you know, class? More, says Kevin. That's right.
What's the tilt of Earth?
23.5 degrees.
Okay.
You should remember that.
Wait, I gave that to you guys as notes, right?
You did.
Okay.
Yeah,
good.
I just signed up for this class yesterday, so I haven't
Caught up to it?
Yeah.
All right.
All the classes are on YouTube, so you can go back and watch it.
And on Blackboard. I post them to the announcements on Blackboard as well.
Oh, okay.
All right,
But either way, or go to my YouTube page. Just don't get confused between the 1010 and 1020 lectures. The seasons will be more extreme than Earth's. Okay, who can explain the why? That's the hard part. Why?
Well, since it's on a more extreme tilt, isn't there going to be a more variation between? I don't really know how to explain it, but
Yeah, see, this is what's tricky. So yes, you're both correct that it's the greater tilt. But I think what we're trying to say is, how do we say this intelligently? How do we explain why tilt causes more extreme seasons? I like when you said greater variation, but greater variation in what? Also, who was saying the greater variation thing? Was that someone I can see here, or was that a hidden person? Oh. Variation in what? Oh, no one feels good about this? Let's look at a
temperature.
Sorry?
The temperature variation will be greater.
Well, the variation in temperature is the seasons, but what is causing the change in temperature? How does tilts lead to temperature?
Is it tilt toward the sun?
Okay, I need a little more than that.
it's going to be in like more direct path of the sunlight. Like since it's on a greater tilt, one part of the Earth or that section is going to have like a more intense season, and then the other side is going to get even less, but like more of a greater magnitude. I don't even know how to explain it.
So that's one of the, one of the reasons we do this exercise is you don't really think about it because you can understand what's going on, but you quickly realize that describing it elegantly, or even to say it correctly at all, is actually pretty difficult to do. And so you have to practice this. I liked it when someone said variation, and I liked it when you talked about the sunlight. Here's how I would put it if I was going to say it as cleanly and simply as possible. You guys tell me what you think about this. This is because the greater tilt will cause a more extreme, I like when someone said variation, but it's variation in the angle of the sunlight. More extreme variation in the angle of sunlight on the Earth. Leading to more extreme variation in temperature. Sometimes in science, you want to be a little bit of an egghead and you want to really explain something carefully and thoroughly so that there's as little ambiguity as possible. So this would be a whiz-bang answer. You guys can copy it all down verbatim. We're doing this together as a group, okay? That's the idea. And you've just earned 5 out of 5 points. You've completed 1 out of 5 homework problems. Yay. 1 down, 4 to go.
This has to do with that. Remember how I was getting messed up with like the sun hitting like the certain, like we'll say the squares of Earth, and like I'm not gonna say it right, but like the intensity.
Yeah, the picture that we
with the lumens, I think.
Well, you can think
over
about it
the summer.
You can think about it in terms of power.
Yeah, because if they're both putting the same amount of power down, light output, it's going to be stronger with the example on the left because it's pointing directly at it. But if it's at an angle, it's getting spread out more because the disbursement of the lights on a bigger area, right?
Right. And as any person who installs solar panels knows, sunlight, perpendicular sunlight, after it goes through our atmosphere, delivers 400 watts per square meter to the ground. If that 400 watts is concentrated in an area this small, that area will be warmer than spreading the 400 watts over a surface this great here. So obviously, if it was perfectly horizontal, no light would strike the surface at all, and then you'd get no heating. Okay, can I erase, or are some people still copying this stuff down?
I'm still copying it.
Okay, that's fine. Just will you let me know when you're done?
Yes.
By the way, bust out your Casios. You're going to be needing them. I think there's a couple of word problems, and then there's a few calculating problems. How are we doing? Whoever you are. Oh, are we good? Was that you, Jake? Oh. Oh, Cam, I'll tell you why your Casio isn't turning on. It needs sunlight. Watch this. Ready? I cover this, and a few seconds later, the Casio dies because it doesn't get any light. Well, especially if I start doing stuff. See, there it goes. It's dying. Turn the lights on in your bedroom, buddy, and it will come back to life, right? Okay, I'm erasing now. No kidding. Okay.
Thanks a lot. Interrupting the fucking lesson with all your dumbass. Oh.
What?
Sorry. No, sorry. No. I wasn't talking to you. I didn't realize it was on.
Nice.
No, I wasn't talking to you at all. I'm sorry about
that. You might want to mute yourself until you're ready to contribute something a little more nicer to the class.
No, I didn't mean that at all. I was talking to
I know,
someone
it's
else.
fine, buddy. It's fine. I don't care. I don't bruise easy, okay? Chapter 2, number 48. Okay, so, hey, Alex of Alex and Jake, you want to read me one of these questions or what? Have you got them handy?
Sure thing.
Okay, so what does chapter 2, number 48 say? And read me the little title. I'm not even going to acknowledge that.
It says farther moon.
A farther moon.
Okay.
All right, read it out.
Suppose the distance to the moon were twice its actual size. Would it still be possible to have a total solar eclipse? Why or why not?
They want to know about a total solar eclipse.
Good job, Alex. Right.
And they want to know why or why not. All right. So there's two sub-questions here. I'm just getting all the givens down onto the page. Class, we need to have an extensive discussion about eclipses. There are several different types of eclipse, but you will at least remember that in our previous lecture, I did show you a picture and explain the concept of a total solar eclipse. That's where the disk of the moon blocks the disk of the sun. And you can see that here in this legendary image from our most recent solar eclipse. Okay, so what do we think? If the moon's twice as far away in a hypothetical solar system, will I still have a total solar eclipse? Sorry?
No.
No. Okay. No. If the moon was twice as far from Earth as it is today, a total solar eclipse. This is a particular type of solar eclipse. A total solar eclipse would not be possible. Why not?
It would have a smaller angular size than the sun.
Bang! That's what I wanted to hear. I was hoping someone would use the term angular size, and you did that just right. This is because... Hey, by the way, who said that? Who contributed that answer? I just want to know who I'm talking to.
I did. Christian.
Oh, Christian. Okay. Christian, since you're so good, can you guess what the new angular size would be?
It would be half. It would be 0.25
units?
Degrees.
Very good. Nicely done. That's the kind of nice little detail we want. This is because the angular size, and that's the key term here, of the moon would be reduced. And since Christian could figure it out in his head, we'll write to 0.25 degrees in parentheses. Little details like that really jazz up your answer. It would be reduced to 0.25 degrees and no longer cover the disk of the sun. Now, our answer is complete here, but while we're doing it right, let's just add one more little detail just to really make it nice. Instead, you would get, what would we get instead? What kind of an eclipse would be possible?
Partial.
You would be able to get partial eclipses. That's not wrong. But if they were perfectly aligned, it would look like this.
I forget the name of it, though.
Yeah. I was trying to see if anyone could remember the name of this. No one knows what that's called?
You tell us
Isn't
it.
it something like post-eclipse?
Annular eclipse.
Annular, yeah, that's right.
An annulus, in Latin, an annulus is a ring. You would get an annular eclipse. But yes, Joel, you would also get partials. It's hard for me to write when it's so far down here. Let me try this. Annular eclipse.
Would it be 0.25 degrees or would it be a arc?
Well, I'm underlining some key terms in there. Cool. Another problem down the hatch. I noticed that my just trying to position this right here. Okay. Take a minute to finish that up before I erase it. Are we good? Mm-hmm.
Is the angular size of the moon measured in degrees, or is it the arcmin kind of thing?
Well, you can do either. In the same way, if I wanted to, I could measure the length of this marker in either inches, or I could measure it in centimeters. When you measure it in degrees, the angular size of the moon is half a degree. When you measure it in arc minutes, it's 30 minutes of arc.
Okay, thank you.
Now, Brendan.
Yeah.
The angle wouldn't change, right?
The angle doesn't change, the units do, and the numbers do correspondingly, right? But
Well,
right? Don't get yourself confused. I used to live next door to this old man named Mr. Matramallo, right? And me and my brother would play like kickball or something, and then the ball would roll into his yard, and he would take it. But before he threw it back to us, he'd go, "Hey, kid, is it shorter to New York or by car?" And we would sit there going, "Is it shorter to New York or by car?" Don't Mr. Matramallo yourself here, okay? It's easy to be confused. Chapter 2, number 53. Okay, what's the title here? I don't know. Who wants to read? Gianna, do you want to? I'm just picking random people that I can see. Gianna, I see your face. Will you read us the problem?
Sure. It says arc minutes and arc seconds. There are 360 degrees in a full circle. A, how many arc minutes are in a full circle?
Okay,
B, how many arc?
Gianna, let's just start with, I'm going to pause you for a second. So Gianna's read the givens. The givens are 360 degrees is one circle. It's important that you guys format your answer just like the problem is formatted. So for part A, it asks, find the number of arc minutes in one circle. All right. We're going to need a technique to do this. Does anyone know what I'm talking about? The technique that we learn in class? Okay. Say it again. Say it loud. Say it proud.
Dimensional analysis.
That's right. And what's the first step in dimensional analysis? Read verbatim off your notes. What's that first step?
Write down the number to convert with its units.
Okay, could you tell me, is that Noah that I hear out there?
Henry.
Oh, Henry. Sorry, Henry. Henry, what should I write down?
You want to convert arc minutes to degrees?
I would actually say it's the other way around.
Or yeah.
Your givens, Henry, are what you're given to start with. And you'll notice when I'm solving problems, I always write down the so-called givens right onto the paper. We want to find the number of arc minutes in one circle. We need to know how to start. And according to Henry, we have to write down the number to convert with its units. But Henry, what is that number?
360 degrees, 2.
Now you're talking business. Let's write that down. Okay, Henry, I'm enjoying talking to you so much, I'll ask you the next question. What's step 2 of dimensional analysis?
Multiply by division bar.
Can handle that. What's step 3 of dimensional analysis?
Put units in first and then cancel.
Put units in first to cancel. Henry, this is your moment to shine. This is the most important part of dimensional analysis. I want you to give me some units top and some units bottom.
Up top would be degree, and then the bottom would be arc minute.
Now,
and 1/60.
Nope.
Epic fail, okay?
Isn't the degree on the bottom and the arc
Yeah.
minute on top?
Yeah, is that Bella that I just heard there in the
Yes.
shadows? Bella, drop some knowledge on these bastards here. Right? So
the one goes on the bottom.
Right, but no, before the numbers, Bella, there's kind of a bigger issue.
Yeah, you can't cancel the degree in the arc minute.
If
You
I
have to
were
cancel both
to
degrees.
multiply these together units wise, I would get degrees squared per arc minute, which is not what I want. So Henry, you just learned an important lesson. What goes top and bottom should be driven by what you have here on top. If degrees are on top, we put degrees on bottom to start. And only by putting degrees on bottom can you cancel out degrees. Arc minutes go on top. So Henry, you learned an important lesson. That's totally cool. Just internalize it and don't make that mistake again. Now, which numbers go where again, Bella?
It's the one on the bottom. Is 1 degree equals 60 arc minutes.
And Henry, you were at least consistent there. You put the 1 with the degree, that's good. But the units have to go in the right spot. Okay, take your calculator, punch them up, tell them what you got.
My calculator is not working.
Who's that?
Andrew.
Andrew, can I see you right now? Wave at me. I can't see your video. I see.
Oh, you can.
Oh, Andrew. Hi, Andrew. I see you now. Sorry. There's so many of you. It takes me a minute to figure out who's talking to me. Andrew, it looks like it's reasonably bright in your room. Can I look at your calculator there? Okay. Do you have a phone on you?
I do.
All right. Here's what I want you to do. This is a test, okay? So check me out here. Watch what I do.
All right.
You got a flashlight tool there, right?
Yeah, I got it.
Put the flashlight up on the solar panel. Does your calculator turn on when you do that?
No.
Fuck. Then you are truly hosed, because that should be plenty enough light to, okay. So what are we gonna do? So your calculator's just totally foobar, just busted?
I guess so.
Wow. Okay.
I hit the button.
Have you hit all the buttons? Mash the button.
I've hit all the buttons.
I'll have to say, this is a first for me, but it's possible, right? In my livelong years of forcing people to buy Casio FX-260 solar calculators, never once has it ever failed. So this is but sooner or later it was bound to happen. Andrew, you're gonna have to make do today. You can rely on us, but you can try to punch along on your phone. Luckily, the calculations aren't too complex. But maybe, where'd you get it from? Walmart or something?
Yeah, I got it from Walmart.
So you bring it back and you say, listen here, jerky, this thing is busted. I paid good money for this thing. Now I want a new one, and get them to replace it for you, okay?
All right.
Go drop some Karen on them, all right?
Because it was working last time I was on here.
Say you want to talk to the manager, all right? Anyways, Andrew, my heart goes out to you. You know, bury it in a little mound out in your backyard.
Oh, now it's working. It's working now somehow.
All right. I don't know. So keep some light on there. If you have a good lamp nearby, make sure it's got some good sunlight. Maybe throw open those or something, okay?
All right.
Anyways, that's pretty rare for a Casio to die. What do you guys get when you multiply them? Anyone at all?
I got 21,600.
And the units?
Oh, minutes of arc of angle.
That's what I got.
What were the units?
Oh, arc minutes.
Arc minutes. Box it up, because that's a classy move. Okay, Gianna, read us part B.
All right. How many arc seconds are in a full circle?
Arc seconds. Okay. There's a couple of different ways to skin this cat. What do you guys think we should do?
I'll try it.
Okay.
You're going to use dimensional analysis, but you have to set up 2 because it's like 2. You're going from minutes to seconds.
Yeah. Well, so this is kind of like a choose your own adventure. I'm curious to see which way you start. What do you want to be? Wait, first, who am I talking to so I can learn everyone's name? Who am I Oh, Katie. Yes.
Katie.
Katie. Which number do you want to start with?
Well, I want to put down what I know. So 360 degrees.
Okay. Yep.
And then times the 60 arc minutes.
Wait. No. Slow your roll there. You are not allowed to talk numbers to me until your units are in place.
Okay.
Only once we got units can we do numbers.
Okay. So I want my 1 degree on the bottom.
Wait. No. You're doing it again. This is
sorry.
This is important. No numbers. Only units.
All right. So I want degrees on the bottom, and I want
arc minutes on the top.
I think she froze.
I think so.
Katie, I think you froze on us here. Where are you? Oh, I think we just lost Katie. She just got taken out of the matrix there, okay? Oh, Katie, are you back?
I'm back. I'm back. My internet just cut out.
Yeah, I could tell. All right, Katie, so what were you saying then? What kind of units do I want here?
Arc minutes on top and degrees on bottom.
Good.
And do you want me to give you numbers or go to the next?
That's optional, but just to prove that we could do it that way, let's go to the next one. I actually like getting all my units set up sometimes.
Then I would do arc seconds on top and arc minutes on bottom.
Yep. Arc minutes on bottom, arc seconds on top. And that will cancel out the arc minutes. Okay, now at the end, we'll put in all the numbers. I kind of like to do it that way sometimes.
Okay.
So.
Do you want me to do it?
Yeah, sure.
So it would be 60 arc minutes over 1 degree.
Correct.
And then the next one would be 1 arc second over 60 arc minutes. And it would give you, once you multiplied across and then divided, 360 arc seconds. Is that right?
No, it sounds weird.
Right now.
A little bit bigger.
Yeah, hold on a second. Katie, something's gone wrong.
Wait.
You made another very instructive mistake here. These mistakes are very instructive for the class. Joel, you hush down for a second. Can the rest of you, and Bella, you too, no telling them what's up. Guys, what happened here? Something went wrong. Who can see it?
You got the same number as you started with?
Yeah, no, I'm sorry, Heva, that's not correct either. It's not a failure of answer. It's a failure of procedure. Where did we go wrong? We did something weird somewhere.
Do you put the 21,600 arc minutes on the bottom?
No. Inside here, we have to use conversion factors. Our conversion factors are 1 degree is equal to 60 arc minutes, and 1 arc minute is equal to 60 arc seconds. Something went wrong with your conversion factors. I want one of the new students to figure it out.
The second division bar should be 60 over 1.
Who said that? Where are you?
Henry.
Henry understands because he's already been burned, okay? I think that was Henry that got burned. The place where you went wrong, Katie, and it can happen to anyone. I've seen people do this hundreds of times. Sorry, I'm just clicking around looking for Katie. Oh, there she is.
I have it in my notes wrong. That's why. I wrote it down last week.
Got to keep the number with the units. It's in a different situation. It could be the 60 on the bottom. I don't think you have it wrong in your notes. You have it wrong in your mind. 1 arc minute is equal to 60 arc seconds. You need to keep the number next to the tag. Sometimes the 1 is on top and sometimes the 1 is on the bottom. In this case,
so I literally wrote arc seconds beside the 1. and I wrote arc minutes beside the 60.
Oh.
So I literally wrote it wrong.
Well, then it's a good thing we discovered
Bless you.
that, isn't it? That's a very good thing.
Yeah. So I just changed it, so I'm good now.
All right, that's great. Okay, so what's the answer then?
I have 1,296,000.
Don't we have some kind of rule about numbers in the millions or something like that?
Oh, you have to convert them.
Not
You have-
convert.
Oh,
Simplify.
notation, scientific
We
notation.
need scientific notation, Andrew.
Yes.
So someone give me the answer in scientific notation. The answer was correct. I just want it in scientific notation.
One tenth to the 9th power. I could be wrong.
Wait.
More sig figs.
1.3 times the 6th.
We can actually keep more sig figs here.
1.29 times 10 to the 6th.
That's good. That's what I want. Does anyone understand? Wait, was it 1.296?
Yeah.
Yeah, so it'd be rounded up.
Which is why I think Andrew said 1.3, or whoever said that.
I did.
Okay. I got to drop some level 2 knowledge on you here. But for me to be able to drop some level 2 knowledge on you, you have to kind of have level 1 knowledge. And I don't know how many of you got that. Sig figs. Some soul proposed that we round this to 1.3. In general, that's not a bad idea. But here, we can actually keep more precision than you think.
Why?
How many sig figs does this number have?
3.
False. Well, actually, no, you're kind of right. In general, the number 360 has 2 sig figs, and the number 60 has 1 sig fig. But in the case of these conversion factors, these are exact conversion factors. By definition, there are exactly even Steven 60 arc seconds to 1 arc minute. For instance, if you have a circle and the diameter is 4 inches and you divide it by 2 to find the radius is now 2 inches. But the radius is exactly half of a circle by definition, right? So 2, if you divide 4 by 2, that 2 is not a significant number. The radius is exactly half of a diameter by design. There are exactly 60 arc seconds in 1 arc minute. So there's infinite precision there. And that means there are exactly 1.296 million arc seconds. I'm guessing that not everyone understood what I just said there, but maybe a few people do. If you are one of the people that understand, then you've learned something. If not, don't worry about it. Just copy it down and let's keep moving. Okay, who is that person again? Huh? Oh, yeah, Gianna. Gianna, what's up with part C?
The moon's angular size is about 1/2 degrees. What is this in arc minutes and in arc seconds?
Okay, Gianna, do you know what to do? If you don't, then just start with the 4 steps of dimensional analysis and read them out with me.
Okay. So you would put...
What is step 1? Just read it out loud.
I don't know.
Do you have your 4 steps of dimensional analysis? This is important.
What I did, let's see, go back here.
I had you put 3 big stars next.
Yeah. Yep. Write down the number to convert with its unit.
So what number should I write down?
0.5.
0.5. You're missing something.
Degrees?
Yeah. Good. Already did that. Okay. What's step 2?
Oh, okay. Multiply by division bar.
Fine. So, I can handle that. What's the third step?
Put the units in first to cancel, so degrees goes on the bottom.
Correct. And what goes on the top?
Arc minutes.
Fine. What's step 4?
Put the numbers in second using conversion factors.
All right. Give me a number on top. Give me a number on bottom.
'We're gonna put 60 on top and 1 on the bottom.
Good. Okay, multiply them up, and what do you get?
$30? Oh.
30 what?
Yeah. 30 arc minutes.
Good. Put a box around it. Okay. Somebody else. Adam, you want to try it? Adam, what do I do next? Are you?
I finally unmute. Sorry.
That's right.
Are we looking? I'm not quite sure actually.
Sure. So we got the moon's angular size in arc minutes, but they also want it in arc seconds. So I need you to do another one of these jobbies, converting that into arc seconds. And if you're feeling unsure, then here's how you proceed. Read me the 4 steps of dimensional analysis. So find them in your notebook, look for the 3 stars, and then we'll just read them together and we'll do whatever the hell it says.
Okay. So write down the number of convert with its units.
So what should I write down?
30 arc minutes.
I like it. What's step 2?
Multiply by a divide bar to put X with the line.
Yep. Okay, I like that too.
Then put your units. So the arc seconds on the top and degree on the bottom.
Hold on a second. I don't like the way this looks. I don't think I'm going to get a good cancel here, right?
Oh,
minutes.
on top it would be arc minutes, not arc seconds.
No, it's not. It's
Which
actually
means-
arc second on top and arc minute on the bottom.
Right. So Adam, let's see what happened here. Let's analyze this. You got to remember that you're trying to get to arc seconds. You're not trying to go back to degrees, right? First of all, here's the first way you should think, Adam. Whatever unit you have on top, you absolutely need to have that unit on the bottom. Here and here always need to match. They need to match so that they cancel out. The second part is to ask yourself, what am I trying to get to? In this case, arc seconds. That goes on top. Okay, what's step 4, Adam?
Put numbers in second using conversion factors.
So there's your conversion factor. Give me some numbers top and bottom.
60 on top, 1 on the bottom.
Correct. Okay, now punch them up and tell me what you get. 30 times 60.
I got 1,800.
Arc seconds, right?
Yeah.
Okay. 1,800 arc seconds. Box it up. Okay, so that was your first attempt class at using dimensional analysis to actually do some conversions. Please be wary. Dimensional analysis is not as easy as it seems. It's always possible to screw it up if you're not careful. It's something that you have to learn over time, and you will learn it because I will make you learn it. That's a third problem down the hatch. Finish copying, and we're going to move on to the next one. Give me 1 sec, class. This, my friends, is a Hungarian wax pepper. They are delicious and tasty, but I should not eat them on my sandwich anymore because it really burned my mouth off and now I'm dying. All right, let's move on to the next problem. Okay, all right, number 57. So Christian, are you down to do some reading with me?
Sure.
Okay, so why don't you read me what number 57 says?
All right. Sun diameter. Use the sun's approximate distance of 150 million kilometers and an angular diameter of about 0.5 degrees to calculate the sun's physical diameter.
How many zeros per million, Christian?
How many zeros? 6.
So let's write this as 150 million kilometers. And what was the angular size?
0.5 degrees.
Okay.
Angular. Sorry. It says, yep, 0.5 degrees.
They said angular diameter because they're lame. I don't like that term. I like angular size. Okay. That was shame on them. They had their grad students write that. All right. Okay. So, and we have to actually do 2 jobs here. We have to find the diameter. And then I think I cut you off, so I'm sorry, but didn't it say we have to compare it to the book's value?
And then compare your answer to the actual value of 1,390,000 kilometers.
No. 1 million. Oh yeah, sorry, yeah. 1.39 million kilometers. Fine. All right. Notice I put it in scientific notation because I don't mess around once it's over 1 million.
Okay.
How are we going to do that, Christian? I'm feeling confused here. Do you know what to do here, Christian?
Let me see here.
If only I had a way to calculate a diameter based on angular size and distance, that I would know what to do.
Is that the small angle formula?
Oh, yeah. Well, how's that sound? How does the small angle formula go?
It says size is equal to the angle times the distance times 2 pi over 360 degrees.
Sounds like a good idea. This is the so-called small angle formula. We're going to use it a whole bunch, okay? Diameter or size is angular size times distance times 2 pi over 360. Our distance is in kilometers, our angle's in degrees. I think we're kind of good to go. Let's plug it in. So the size is 0.5 degrees times 150 million kilometers, right? Times 2 times pi over 360 degrees. Okay, I want everyone to punch and crunch here. No slackers. Everyone's got to punch this in because it's good for you. And because it's your first time doing a longer problem together, I'm going to punch alongside you so you can follow me, okay? We're going to do it all in one clean shot. Oh, by the way, let's talk about pi for a second. Do you guys see the EXP key here? Let me focus. Let me see if I can bring it in here a little bit. Oh, yeah. Whoa. Okay. Can you guys see how pi is above the EXP in gray? Most of the time, when you have a number above these keys in orange, you've got to hit your shift key first. Like to square root, you have to do shift square root, okay? But pi is a special key and it's weird. Now you could hit shift and then EXP and you'll get pi 3.14159265354. But because pi is in gray, sorry, I'm just trying to make this straight with the camera here. It makes me realize that this whole damn thing is twisted. Okay. I can just hit EXP and get pi. So EXP is like a very delicate samurai sword. You have to know how to use it. If I hit 2 EXP3, EXP is 2 times 10. But if I hit clear 2 times EXP, it's going to multiply it by pi. In any case, why don't you guys just follow along with me here, okay? We're going to do 0.5 times 150 EXP6 times 2 times pi divide by 360 equals. Everyone, hold up your calculators to the screen. Show them what you got. I want to see who's doing good. Gianna, I like it. Kelly, I like it. Jake, I like it. Andy, yes. Adam, yes. Donald, yes. Alicia, yes. Tristan, yes. Yes. Henry, you got it. It looks like everyone's getting it. Even Nicole with her wacky phone calculator has it. Nicole is just dying.
I don't know how you get pi. I'm confused.
I got lost.
Okay, let's try one more time. The way you get pi is just by hitting EXP. So Andrew, watch me again, okay? Everyone else who has it, just sit tight. Andrew, watch me. 0.5 times 150 EXP6 times 2 times, when you're ready to hit the pi, you just hit EXP, times pi, divide by 360 equals. Did it work this time, Andrew?
Yeah, I got 130.
Hold on, you didn't get 130. What is that number?
Oh,
it ain't 130.
13 million.
Not 13 million.
130,000?
No. Look.
Oh wait, it's 3. It's 3. I'm trying to figure out. Oh, it's 1,380,900.
Okay, let's round off. Let's keep 3 sig figs so we can compare to the book.
All right.
So how would I do this to 3 sig figs? And I should put it in scientific notation too.
Yep.
1 point. Well,
would it be 30?
Well, you got to do good rounding, right? If you're chopping an 8, is 8 cents closer to a dime or 0?
A dime.
Yeah. So you got to do 1.31 times 10 to what power?
To the 6th.
Good. And what are the units?
Kilometers.
Kilometers, because degrees on top here cancels with degrees on bottom there, leaving behind kilometers. Box it. The better way to say that is 1.31 million kilometers. We've gotten 4 out of 5 points here. We've got one more point to earn. It's time that we compare to the book. In this class, compare means something very particular. Compare means take the ratio. Obviously, the book's value is a little bigger than our value, but I want to do something quantitative. I'm going to divide the small one by the big one. So I'm going to divide the size of the sun by the size listed in the book. I'm just going to take a ratio. So I'll do 1.31 million kilometers divided by 1.39 million kilometers. This is how we play. What do you get? 2 sig figs are fine. What do you get?
Got 0.94, which.
Really?
Yeah.
Why did I get something different? Oh, no, you're right. I screwed up. You're correct. How do I interpret that 0.94? What does that mean?
Can we do 1?
No.
No.
We cannot over round it, okay? Rounding it to 1 would be bad.
Okay.
What are the units of the 0.94?
Kilometers.
False. Kilometers on top cancel kilometers on bottom.
Okay.
Percentage.
It's a percentage. And what percentage is it, Joel?
94%.
It's 94% of the book value. So we are pretty close. We're only off by about a few percent. Okay, that's how you do it. Finish copying that down. All right. We've killed 4 problems. We got 1 left to go. May I erase, class? It takes a little while to do a homework, but I promise you it would have taken you longer to do it without me. 59. Let's see. Okay, so I don't know. I need someone. Who do I see here on the screen? Henry, are you open to reading a problem for me?
Yep.
Okay, Henry, this is the big whopper. This last problem is the hard one. Okay, we always save the hard one for last. Just turn the screw a little bit before we let you go. Okay. Before you start reading, Henry, let me give a little preamble to this.
Mm-hmm.
In the other problem that we just did, you guys learned the small angle formula. And the small angle formula allows you to calculate the size of a star or moon based on its angular size and its distance. Sometimes we don't want to calculate the diameter. Sometimes it turns out that we know the diameter, we know how big Pluto is, but we want to be able to calculate its angular size if we travel to some other planet. In that case, sometimes we have to do rearrangement here, and we have to solve for theta, the angular size. Now we're going to do a little algebra. If I rearrange this equation, I put d on the bottom, 360 on the top, and 2 pi on the bottom. And if I do that carefully, I get this formula. The angular size is 360 degrees over 2 pi times the size divided by the distance. And although this is still the small angle formula, you can think of this version as being the version that is used to calculate angular size. Why don't you go ahead and write that down and put a box around it? Because this is something that not only do you need for this problem, but you're going to need many other times in this class, including wink, wink, nudge, nudge on the test. I'm going to give that marker a little break, and I'm going to get a fresh one. I'm going to freshie out here. See if any of these are any good. All these are a little beat up. Too many damn markers here. Okay, Henry.
Yep.
All right. Henry, read out our problem if you don't mind.
Eclipse conditions. The moon's precise equatorial diameter is 3,476 kilometers, and its orbital distance from Earth varies between 356,400 and 406,700 kilometers.
Okay, Henry, pause there for a second. I got to catch up to you. First, let's get our moon data down. So for the moon, they gave us a diameter of 3,476 kilometers. Is that right?
Yep.
And then what were the distances?
356,400
And
406,700.
And that's kilometers.
Yep.
Okay, why don't you write that down, Henry, yourself, and then keep reading. Now they're going to give us some sun data.
The sun's diameter is 1,390,000 kilometers, and its distance from the Earth ranges between 147.5 and 152.6 million kilometers.
How many zeros are in a million, Henry?
6.
Fine. So let's get that down too. These are your givens. This is a bigger problem than you've had so far, so you've got a lot of givens. Get your givens down before we go further. Henry, when you're done copying, you can continue.
A. Find the moon's angular size at its minimum and maximum distances from the Earth.
Okay, class, I need to erase all this before I go forward because I'm going to need more than that. Can I erase? Oh, Cam just snapped a photo. Greg says yes. Any objections to me erasing?
I'll take a picture now.
Okay. I don't mind giving you a second too if you can do it quickly.
So what are these numbers? These are the diameter?
So yeah, these numbers here, these are the diameter. And here, this is the min and the max distance.
Okay, thank you.
Got to try to keep it all straight. Okay, I'm erasing this. This is all in the problem. I'm just writing down the givens because that's a good thing to do. Okay, what did you say was the thing to do again? Henry, A asks us to do what?
Find the moon's angular size at
What's that crazy fucking noise? That's. Who are you?
I heard it too.
I think it was an echo.
Oh, from Cam, from his headset?
No, I don't think it was me.
I don't think it was you either. It came up.
It's just an echo
My
because
mic was
somebody has
muted.
speakers, so it goes to the mic and it just keeps looping.
Well, just mute yourself if you're not speaking. That's all. That's a good way to solve that problem. Okay. Find the angular size of the moon at minimum and max distance. We're going to stay nice and organized here. The trick is to stay organized and to label everything. First, we're going to tackle the min distance. And we're going to use the angular size formula that we just had. So the angular size is 360 degrees divided by 2 times pi. Up top is the S. So what do I put in for the S, class? Who understands what's going on here? What goes up top?
3,476 kilometers.
I like the units are important, so good job. 3476 kilometers. What's the min distance on the bottom?
356,400 kilometers.
Is that right, everyone? Did I remember that right? 350.
Yes.
All right. Class, we have to talk about how to punch this in. This is a very dangerous moment for the class where many of you are going to get this wrong, okay? I need to talk to you about a strategy of how you're going to go about this, okay? So write that down. Take a second to write it down. I know people need to catch up, and then I want to talk to you on how to do it. Okay. Let me walk you through first how this is going to be punched into our calculator. The real danger is the 2 and the pi. The calculator needs to know which numbers are on top and which numbers are on bottom. Joel, I like your dog. What was that dog's name again? I love that guy.
Fenway.
Fenway. He's a good pooch. Just tails up.
He's bored. He's very bored.
Okay, well, I'm sure Fenway's not alone in his boredom here, but we're almost done. So just bear with me, Fenway. Okay, we are going to punch in 360. We are going to divide by 2. Then we're going to divide by pi. Then we're going to multiply by this. And then we're going to divide by that. So it's going to be times, divide, divide, times, divide. Anytime something is on the bottom, you have to divide separately. So I want you to punch along with me. Everyone start off and do 360. Then divide by 2. Then divide by pi. Then times 3476. Then divide by 356, 400, and then and only then hit equals. This is what you should have. Hold them up. Show me what you got. Hold on a sec here. Yin, good. Bella, good. Donald, good. Tristan, good. Kelly, yes. Greg. Juan, you're a little far away, but it looks like you got it. Yep, Juan, you're good. Christian, yes. Alex and Jake, looks Jake, you're a little off the screen, but I'm guessing you got it. How could the twins have different answers? That would be crazy. Adam, yes. Gianna, yes. Andy, yes. Joel, yes. Henry, I think so. You're a little far. Yeah, Henry, yes. Andrew's good. Katie. Oh, you guys are awesome. And even Noah there has it. Okay. Cam, I like it. Okay, so everyone, you guys are good at following instructions. Hey, now it's time for an adult conversation. I was talking to someone about this earlier.
Wait a minute.
Oh, yeah? Joel?
Was the answer 0.55 something?
Yeah. Is that not what you got?
No.
All right, so we got to try it again. Joel, no big deal. You punch again, okay? So it's 360. I'm going to go quicker this time. Divide by 2, divide by pi.
Oh, damn it. That's what I did wrong.
Yeah.
I multiplied by pi.
Nope. Divide by pi. 3476 divided by 356, 400.
That's what I did wrong.
All right. Now listen, guys. How many sig figs do I get to keep? How many sig figs are limiting in this problem here? 362 and pi have infinite precision. These are measurements. How many significant figures?
4. There's 4 up top and 6 on bottom.
I'm sorry, whoever's in the background there, what did you say?
4 is the smallest number, so I believe you go with the smallest number.
Correct. They both have 4. This has 4 and this has 4. So whoever I'm talking to there, what should I round my answer to then?
4 sig figs. I just took my answer off though. So.
Why would you do that? We're still okay. So
I don't know. I don't know why I did that.
All right. Well, look at mine. What should I keep then?
I can't see it. It's going to be 5588, I think is what I can see.
0.5588. What are my units?
Kilometers?
No.
Oh, no. Never mind.
What are my units?
Is it degrees?
Yes.
Degrees, yeah.
It's an angle after all. Okay, now we're going to do that again. The max distance. Hopefully this will go a little faster now. The angular size is 360 degrees over 2 times pi. Same diameter, 3476 kilometers. But now we use the max distance. Who can remind me what the max? It was 400 and something, right?
406,700.
Okay, class, punch them up. Tell me what you get. Punch them up. Come on, guys. Fenway's getting bored. He needs a run.
Brendan.
Yeah, Joel, that looks good. Donald, like you're a little in the shadows there. Kevin, that sounds good too. Kelly, I like it. So, someone shout out the answer. It looks like several of you have it. What should I round it to? Yes. You're all looking good. What should I round my answer to?
I always keep on forgetting about the EXP with the pi.
Oh, right. If you do divide by EXP, if you hit EXP by itself, it's just
Oh,
pi.
yeah, I did that. All right.
So what, okay, Christian, I like it. So what do I do, Christian?
360.
Christian, what should I round my answer to? Anyone? Oh, I know you have it on your calculators. Just tell me what to do.
Sorry, I was muted. 0.4897 degrees.
Did you round proper?
Yes, I believe so.
Fine. Box it up. No, oh yeah, you did round proper. Good. All right, killer. I need to erase. We got to move on to part B. Henry was the reader. I'm erasing. Actually, I'm going to erase strategically. Strategic erasings. Henry, what's part B say?
Find the sun's angular size at its maximum and minimum distances from Earth.
Second verse, same as the first. A little bit longer and a little bit worse. We need the diameter of the sun. What was the diameter of the sun? 1.39 million kilometers. I gotta Windex this board later. Okay. What is the minimum distance to the sun?
147.5 times 10 to the 6.
And what was the maximum?
152.6 times 10 to the 6.
Sorry, I kind of squeezed that in there. Hopefully you guys can read that. Okay, punch them up. Punching is a you job. Now, I was talking to someone in the background. I don't know if that was Katy or if that was someone in the shadows. Katy, what's my limiting precision here?
Are you asking me for the sig fig?
Yeah,
It's gonna be 3.
exactly. So this time we're gonna have to round to 3. Do you guys know what you're doing here? God, I miss having tutors. I used to have really smart tutors. They would help me with all this. What's the first one?
Is it 0.539?
Round better.
0.54.
0.540 if you're going to keep 3 sig figs.
Oh, I keep on messing up on that.
That's okay. It takes a while to learn. The idea is that this 0 is not a sig fig. If you're going to round 0.5399 to 3 sig figs, this 9 makes 39 into a 40. But you got to keep that 0 so that you still have 3 sig figs. That was a tricky one. Someone get me the next one.
I didn't get that, the first one for the thing, because what I got from my answer is 0.528.
Well, someone hit a funny button. Let's see what happened. Watch me, Bella. 360 divided by 2 divided by pi times 1.39 exp6 divided by 147.5 exp6 equals. Did it work better this time?
Yeah.
You hit a funky button somewhere.
Yeah, I did.
Okay, someone do the next one for me.
For the next one, it'd be 0.523.
Okay.
Messing up on that pi.
I think it's 0.522. I don't know.
Yeah.
What's the number? All right, what is, give me it to 4 sig figs. 0.52.
1.18.
So that makes it 0.522, right? Because the 8 rounds the 1 to 2. All right, write it down. We got one part left, part C.
I got a really funky number, but okay.
Okay, let's help you. Do you want to watch me do it?
I keep on messing up on these.
Yep, you got to use your EXP and you got to divide by 2. You got to divide by pi. The easiest way is for you to just follow me, okay?
Okay.
360 divide by 2.
Okay.
Divide by pi.
Divide by pi. Yep.
Times 1.39
1.39
exp6
6
divide by 152.6 exp6 equals.
Oh, there we go.
That work?
Yep.
Yep, I got that.
All right, cool. Once you do it right a few times, you'll start to learn how this works. Let me just check the chat log for any issues before I go on to part C. Chat log says, oh, it's just Kevin giving me the correct answer before. Okay. All right. I need to erase here so I have room for part C. Henry, you're up. What's part C ask?
Based on your answers to part A and B, is it possible to have a total solar eclipse when the moon and the sun are both at their maximum distances? Explain.
Okay. So to do this, sorry, I'm just trying to get some of the gick off the board. You guys can't see it, but my board is getting gicky. Ava, that's gicky, G-I-C-K-K-Y, all right? Gicky is bad stuff. Okay. So part C. Is it possible to have a total solar eclipse when both the moon and sun are at their maximum distances? Weirdly enough, if you think about it, class, maximum distance actually means the minimum angular size, because the farther away a thing is, the smaller it looks, right? Like, here's Moonball. Here it's got a large angular size, and as I get farther and farther away, the angular size gets smaller. So let's round to 2 sig figs to make this easier. What was the minimum angular size of the moon?
0.5588 degrees.
That's 4 sig figs. So that's also its maximum angular size. Okay, y'all fucked up. Y'all screwed up here. You screwed up twice. First, you confused maximum distance with maximum angular size. Secondly, I want 2 sig figs, not 4 sig figs. So once again, what is the minimum angular size of the moon rounded to 2 sig figs?
0.49.
There we go. And that's degrees, right?
Degrees, yeah.
All right, what's the minimum angular size of the sun to 2 sig figs?
0.52 degrees.
So when the sun and moon are at maximum distance, that will be their minimum angular size. Is it possible to have a total solar eclipse under these conditions? Who understands me here?
You can't, because they're not the same.
Yeah.
What do you call it? Angular size. Yeah.
Right? So let's draw a diagram of what's going on there. Here's the sun. And the sun's angular size is 0.52 degrees. And here's the moon. The moon's angular size is 0.49 degrees, right? That's a crappy diagram, but hopefully you understand what I was trying to do there. So let's write something down. No, a total solar eclipse is not possible at maximum distances because the moon's angular size is, let's see, 0.52 minus 0.49, 0.03 degrees smaller than the sun. Instead, you get, what do we call this again?
Annular eclipse.
We get an annular eclipse. This is how we get annular eclipses. Because at the maximum distance, the moon's angular size shrinks to just less than ½ a degree, but the sun stays at ½ a degree. The moon's orbit is slightly more eccentric than the Earth's orbit around the sun. Ta-da! You have completed homework assignment number 1. 25 points for you. Now it's time for us to talk about the submission of homework 1. First, let me make sure everyone's had enough time to capture this and to get it all down.
How do you spell angular? Is it ANN?
Wait, do you mean angular or annular?
Annular eclipse. That one.
ANNULAR.
All right, I got that.
Hey,
I didn't see
Cam?
the V. I thought it was a
Cam.
V.
Cam said he did his homework on Google Docs. Cam, your math better look good in Google Docs, okay? Do you know what I mean about using an equation editor? Cam, did you use an equation editor?
Not particularly.
Well, then I'm going to be pissed off. Do you want me to be pissed off when I'm grading your homework?
Oh, hell no.
Okay, exactly. So Cam, here's what you need to do to clean it up. Hold on, let me try to use Google Docs here. Let me share my
I
screen.
could just show you what it looks like, though.
Yeah, show me.
All right.
I'll give you permission. I've given you permission to share screen. Do you want to just share your screen or what?
I guess.
Or
Let me just close out a few things.
Yeah. Or if you have a better way to do it. Juan, did you have a comment? Who else was talking to me there?
Can I send you the picture like I did last time?
How did you say? Yeah, did you just take a photo? Did you
Yeah,
submit
I
it to
took a picture.
Blackboard?
Yeah, and I submitted it.
Okay, was I happy?
Yeah, you were.
Okay, then yes, you can do that. But taking a photo is easy enough. Cam, why don't I share my screen with you rather than you share your screen with me? Cam, let me go to Google Docs. And you know that last problem that we just did?
Yeah.
And I'm not just talking to Cam here. I'm talking to everyone. Here's what I would expect that to look like if you were doing that. I should be logged in here. This is what I'd want to see, okay? So you'd have chapter 2, number 59, right?
Mm-hmm.
And, you know, when it's time to do the moon, if you're going to show me the equation, which you should do, your equation should use an equation editor, which they should have. How do I insert an equation?
What I just did was insert
okay.
text symbols
So
like
here's,
pi and degree.
There's theta equals, and now we have to go to our division. No, not that. We want a proper ass division bar. And then I should see 360. You should have units of degrees, which you should be able to get from symbols somewhere. 360 degrees. You might have to put that in a subscript. Divided by.
Oh, I did that. Don't worry.
Oh, you made that look all nice and jazzy for me?
Mm-hmm. Yeah. All I did is just copy and paste. I didn't know you can do that with equation editor, actually. All I did was like copy and paste.
Yeah, you want to do equation editor, okay? Oops.
I see.
360.
How do you get the degree symbol to be above the icon? Because I did the same thing on Google Docs.
Let me show you. Watch how I want you guys to watch how I did that. So everyone watch and learn here. This is a teachable moment for everyone. I go to insert equation. I go to my Greek letters. I find theta equals. Now, first of all, I got to find a division bar. So I go over here and make a division bar. Now, I know I'm going to want 360 degrees to be on top, degrees to be on top. So before I type 360, I go to my superscripts. I hit X to the B for superscript. Then I type 360 and I arrow over once. Now it's in the superscript. Now I find the symbols for degree and I plug degrees in. Ooh, look how nice that looks. Now I go to the bottom and I type 2 and now I'm going to do pi. So I'll go over here to my Greek letters, whip in a pi. Now I arrow over. You see what I mean? It better look all like this. Use a proper, and for the math stuff too.
Well,
Wait,
fraction doesn't look like that, to be honest. But
well, then
I'll show you how I did it.
Then I'm going to be pissed, okay? Then I will be unhappy person, and I will be grading your paper as an unhappy person.
But I'll show you what it looks like. I kind of made mine kind of similar to that.
Well, show me. Oops. So
I'm
it's
trying to figure out how to share it.
Nice. That's what the angular size formula should look like, and your math should look like that too, right? Like when it comes time to do it again, you just copy it, you paste it. Yeah, you can show me what yours looks like in a second. And then when it's time, if we were doing the moon, I want to see, 3476 km. It better look like this. You see what I'm saying?
I see what you're saying.
Like I don't want to see 2 times 10 caret 6 kilometers. If your
Oh, I
shit,
didn't do that. I didn't do
if
that.
your shit
Don't
looks
worry.
like this, then we got probs, Bobs. Okay. Okay. All right. So
I'm trying to figure out how to share it.
I was sharing my screen, so I don't know if you want to share your screen. That's one way to do it.
Sure. Sure, but I don't know how to do that on here.
At the bottom, there's a button that says share screen with a little arrow. Do you see that?
Share, yeah, I see it.
Make sure you hide all your inappropriate tabs.
Don't worry, it's all good. I'm not that type of person.
All right. All right. Cam has
But that's
started
what I
screen
have.
sharing. Hold on, I don't see anything yet. Oh, here we go. Okay, scroll down to the bottom problem. That'll really tell me what's up. So far, so good. Hey, wait, 21,6000. Where's your units? Where's the
Wait, what?
Go up, 21,6000. Where's your units?
Oh, I forgot.
Yeah.
Was it kilometers or?
Okay, do you see your sun diameter? Your sun diameter looks like shit. I think you need to you have to use an equation editor. I don't want to see an asterisk for times. I don't like any of your time symbols. They piss me off, okay?
Oh, okay.
Use an X, use a proper, insert an equation. Anytime you do math, you should always be using the equation editor. You might need to take a few minutes to clean yours up. You'll get good at this, that's right. Every time you do math, the whole equation should be in an equation editor. In fact, leave it up so you don't forget what you just did. Control Z that shit. And skip a line, and you have to redo the whole thing in an equation editor. Scroll down. Can you scroll down to the last problem for me?
Oh, yeah, I can.
Sorry, I'm going kind of quick here. Go down. You know what? You made it look, that's not the worst I've ever seen, Cam. Like, I can see what's going on there, and it's kind of okay. But here's a good rule of thumb. So let's stop your screen sharing for a second, okay?
All right, so how do I get out of
I'm going to stop it for you. Hey, Cam.
Oh, okay, thank you.
For a hack job, yours actually looked pretty good, and I probably would have accepted that and graded it, and I would have just grumbled a bit, and I would have cursed your name a little bit, all right? But as we go forward, that level of shittiness is not going to cut it. So what I want to say is this, Cam. Every single time you put any math in from one side of the equals to the other, it should always be in an equation editor. And you should always use all the fancy symbols like times and the superscripts and stuff. And actually, that's good training for your future job stuff too. So that's not going to be a waste of your time. You'll get really fast at it. So
yeah, I didn't know about equation editor until today.
I'll cut a deal with you, Cam. Just to save yourself some time, I will let you submit that, and I'll take it, okay? But from now on going forward, because it doesn't look that bad, from now on going forward, you'll always use the equation editor. Is that a deal?
Okie dokie. That's a deal.
Cool. Now, how about the rest of you? At some point, I want to...
Can you check mine, Brendan?
Yeah, I want to check yours. Can I just talk to you guys real quick about submissions before you go? Sorry. I want to... fuck. That was not what I wanted. Hold on, guys. Hold on. Kick my power supply out. Okay. I'm sorry. I wanted to sit down here because I've been standing for a while. All right. Listen. The first lab, do you guys remember how I checked all of your homeworks to make sure they were good? Your lab submissions, I mean? We can do that one more time with today's homework. I probably shouldn't do it every time because it'll tack on another hour to the rendering of this video. And there are night students that need to watch it as well. But for today, since I've got a few of you still with me, if you guys want to upload it right away and we can take a look and see how, just like I did with Cam there.
I just submitted. Can you please check?
Yeah.
Because I'm running late.
You got to go fast?
Yeah.
All right, Juan, we'll do you first.
Thank you.
Juan, this is your homework right here, right?
Yep.
Okay, so I think if I click on your name. It's still loading, Juan, sorry.
It's fine.
Oh, Juan, this looks great. Let me see how your math looks.
Okay, I just submitted mine.
Oh yeah, Juan, this is wonderful stuff. Okay, so Juan, wait, do you have all the pages? Are they out of sequence or something? Where's that fifth problem?
It's the very last one.
No, I clicked on the very last one.
It's right there. Oh wait. Nah, it took me 2 pages for the last problem.
Okay, they're a little out of sequence, I guess, but that's okay. In any case, Juan, the images show up in the box and they look good and they look neat and tidy. So you are good, buddy, okay? If you got to get to work or whatever, go ahead and do that. 25 out of 25 for you, okay?
All right, thank you.
You're right. Anyone else want me to check out theirs?
You can check mine again if you want. I just submitted it.
Sure. Let me sort these so I can separate the homework from the labs. I noticed a few of you turned in the lab a little late. That's okay. I'm sorry, who just said that? I lost track of you.
Joel.
Joel, we'll check you. There we go. Yeah, bud. This stuff looks good. Oh,
cool.
Thanks for drawing. I appreciate that. Who else wants me to check? Christopher Roberts.
Check mine quick, real professor.
Yep. Who said real quick? Someone's in a rush.
Alex Esposito.
Oh yeah, Alex Esposito. Sure. Let me just erase whatever that stuff was. Okay. All right. Alex Esposito. Presumably, Alex, if yours is good, then Jake's will be good too, right? Because you're using the same methods.
Yeah, and considering you wanted to off yourself last week over mine, I'm trying to have it be a little better.
Okay, cool. So yeah, Alex Esposito. Let's check this out. Oh, it looks like it's good. That's what I want. I want to be able to load them. It's okay if it takes a minute, but I want it to load in this box here. Oh, that looks beautiful. Look at that. Now that's some workmanlike quality. Okay, 25 out of 25.
I'm sorry, my generator is not as good as Juan's.
Okay. No. It looks great. Ava, I'm going to get to you. I'll get to everyone. Let's just check out Ava's real quick because she asked. Ava, am I saying that right? Is it like Eve, but are you Swedish? What are you, Ava? Ava, whatever you are, whatever your nationality is, your homework looks beautiful, okay? I like the little pen boxes. That's a nice touch there, okay? Okay. So Ava's looking good. Who else? Henry Fox. I assume that's Henry, so let's click you. Now okay. Oh yeah, that looks wonderful.
Is there both
Henry,
there?
Pardon?
Are they both there, both pages?
Let's check them both. Yep, beautiful. Right. Nice, neat work, Henry. I like that. Good workmanlike job. Who else? Who else wants to know?
Can you check mine, Professor?
Yeah, who's me?
Oh, Christian, sorry.
Oh, that's okay. Christian. Oh yeah, we had some trouble with yours last time, didn't we?
No, mine was fine. I used a PDF.
Oh. Christian, why don't I see you here? Do you see you here? I don't. Here, maybe I need to refresh the page. Maybe. Now I had 21 submissions. Now I still have 21. Hold on. There's a glitch in the matrix. I got to figure this out here. All right. So let me click this. And let me click needs grading again and see if I have any more. In the future, we'll have this all streamlined and it won't be so difficult. Oh, there you go, Christian. I see you. Christian. It's loading. Oh, I noticed this about the PDFs. Oh, wow, that looks real nice. Beautiful. Absolutely beautiful. Anyone else?
Yeah, can you check mine?
Bella.
I figured out a way how to do it without using my phone to upload.
Oh, cool. Let's see if yours came out any better this time.
I have to do mine through the computer.
Yeah, everyone kind of has their own special method because you're all little special snowflakes and it's different phones and all this stuff. Hey, this looks great, Bella. You're good. Who else can I check?
Professor, could you also check mine? Zach.
Zach. Where is Zach? There we go. Yeah, this is really important because You know how it takes me a long time to grade 160 people? If you all display like this, when I click it, it makes it really easier. It makes it less horrible. So it's important that, yeah, this is great, Zach. It looks like we've
Yeah, it's
worked
just
out.
backwards too. And I put part 2 and then part 3.
That's okay, as long as I can load and I can see that stuff right away. Who else wants to check?
Thank you.
Can you check mine, Katie?
Check mine again if you want.
Yep, okay. Kevin, I can check yours. And Michaela, I'm gonna check yours too. Sorry, all right, so Kevin and Michaela, let me do those two before I forget, because they're on the chat here. So let's see who I find first. Kevin, Michaela, and then I'll get, all right, Kevin.
Just to reiterate, the pages, because mine aren't going 1, 2, 3, it's going 3, 2, 1. As long as you have all 3 working, it works.
Yeah, as
Okay.
long as, here's what I care about, is the order of the pages is less important than, do you see how I just clicked on Kevin's and the box shows me a preview right there? So
Yeah.
I can quickly load it and do it. That's how I can grade you guys quickly and efficiently. What's shitty is if it gets a weird file and I have to click a hyperlink or something like that.
Yeah.
But as long as I can scroll through like this, like Kevin, you're good. Yes, I think it was Katie. I'll check you too. And who's the other chat person?
I could use mine check too.
Okay, and Michaela as well. Sure. Just bear with me. I'm going a little kooky here. Let me just check Michaela's. I'm trying to do this quick because I know you guys have other. All right, so this is what I'm talking about. Michaela, if I'm absolutely have to, I can click on this, but this shit slows me down and I have to open up a new tab. And if people submit while I'm actually, it's not even loading. Michaela, this is no bueno. You gotta figure this out. Can you somehow figure this out? Oh, okay, it did load, but do you see how I had to click 2 or 3 times to get it? That stuff really slows me down. So Michaela, if you can make yours a little smaller, PDFs should display in this box. I suspect that what's going on is you're too high resolution. Not high resolution, but I think the size of your image is too large. I think you need to do this, but you need to scale this down to like 1,000 pixels or 1,500 pixels or something. I think that's what it is. Yin, I can also check yours as well. Hold on, I know there's a lot of hungry birds to feed out there. Just I know I'm not doing this very systematically, but I'll get to everyone.
Mr. Brendan, are we all done?
Yeah, so if I've already checked yours off, in fact, from now that a couple of people in the night class have seen this, let me just stop for a second. I'm gonna check anyone else who wants, but I am about to stop the video so that the video does not go on for too long. So I'm gonna stop recording. Let me say, if you're in the night class, if you're watching later, please submit your homework in a format that I can read and get it to me before Sunday. Okay, peace out in the Middle East.